Good morning, everyone, and thank you for being here so early. So let's start our session. Well, the following of the yesterday's session. So this is on nowcasting and post-processing techniques, systems and products. And we have 4 talks this morning. And the first talk is a keynote presentation by Roger. I will not try to tell your name. And I didn't know that it was, so the title was in a changing climate. I was surprised with yes. This part of the presentation, but okay, I give you the floor, George. So please go ahead.
Thank you, Stefan. Yeah, indeed, this presentation is about on-demand extremes digital twin, and we added it's about extremes in changing climate. And my name is Roger Ndiamampiana, and I will talk on behalf of a large group from ECMWF and also from the what we call on-demand extremes digital twin team, which you can see here, which I would like to thank first. So after a short introduction about motivation, I will introduce the digital twin of the Earth. And then the main part of this presentation will be about the digital twin, on-demand extremes digital twin. I will talk about some quality assessments and some uncertainty quantification development. And then I will give some conclusions and talk about the vision about the next steps. So I think it's really, we are living in very, very challenging moment with a changing climate. Day by day, we follow on the news different events that are not slightly, but very different from what we used to see. So here, for example, since we are in Norway, we learned about the storm Hans, for example, 1 year ago. You can see here a railway bridge broken, and it took some months to put it back on track. And someone built their properties, never thought about to find it floating on the river sometime. Next picture is showing one small city in Norway. People settled there. And this is completely inundated. And it's turned out that, sorry, after this event, some of these properties could not be used right away. So yeah, and peculiarity of this event was also that the amount of water so big, so it took some time to really get out of the country to the seaside. So with a lot of damages and a lot of economical consequences. And we just learned recently also about the storm Boris, although relatively well forecasted, but still we can see here, left-hand side, there are still some consequences in Poland. Right-hand side, you can see the one city in Czech Republic. And we also learned that even also in Italy. So it was quite a strong storm and passing through a lot of countries. Now I would like to borrow some slides from my director to talk a little bit about what's happening and what should be done. So he said that the severity of the events exceeded our expectation. And why is that? Because people base their interpretation of the forecast on how they were affected in previous events. Good. And the formal definition of the extreme event is actually based on a threshold relative to what is called normal. And the interpretation of what is extreme is individual and based on context. So we know that weather and flood forecasting is not accurate enough. Otherwise, could have been already fired. And the consequences of the events is not sufficiently explained or understood. Here we can talk about also the importance of the uncertainty accompanied with all of these forecasts. But even though if we give really a reliable uncertainty, but still it can be still misunderstood by people. So what we can do to really minimize this kind of consequences. So here Ruar mentioned that about mitigation, we are running late, but every improvement, every trial counts. We can prepare about what action should we take when we receive the forecast, hours or days ahead of the event. We can also handle what action should be taken the first hours or days after the event. But there is still something that we can still do, so adaptation about what measures should be taken for the next 5 or 10 years. And here we can mention one of those, European-wise decision from the European Commission to build the destination Earth infrastructure and service. They asked the so-called 3 E's, so ESA, EUMETSAT, and ECMWF, to build that infrastructure and service. And ECMWF was asked to build the destination digital twin of the Earth. So what is a digital twin? Digital twin should comprise in itself both scientific and technology capabilities, latest, I would say, including machine learning, and importantly, it should also comprise in itself the sector of socio-economic impacts. So what does it mean for us? We need to build physical and data-driven weather models and build the workflow and co-design it and co-create it with users and with strong involvement of impact sectors. So the first 2 digital twins in Destiny are the climate change adaptation and the weather-induced extreme events. The weather-induced extreme events has 2 components, a global one, which is built by ECMWF, and the on-demand one, which is built by the team, as I called earlier, or under the project called D330 and led by Météo France, with 31 partners. It's quite a big in both phases 1 and phase 2. So what is different in these digital twin services? So in current situation of a weather forecast, we still have a limited resolution, around 10 kilometers globally, and 1 to 2.5 kilometers regional in regional scale. We do operational production of daily forecasts with fixed configuration, domain, and outputs. And I think one of the important one is the separation of the Earth system model and the impact sectors. While the digital twin, now it's start with a resolution at 4.5 kilometer globally, and then sub-kilometer regionally. So having an operational capability to run simulation both regularly and also on demand for past, present, and we are thinking about also to have it for a future event. Having a flexible configurations, but domain, output, allowing to respond evolving extreme events by triggering tailored simulation and create, most importantly, information co-created and co-designed and fit to purpose with the users. bringing the Earth system model and impact sector within the same workflow. And so if we can say in phase one, we were building the different Legos of the workflow. Now in phase two, we are trying to put together the different Legos and see if we have a picture we wanted. So definitely we need, for example, for the on-demand system, we need a detection system which is triggering with configuration. And that is actually connected with a duty team, I will talk about that later, to the digital twin, which comprise, as I said before, weather, impact, and post-processing components. That will then deliver information, tailored information to the data bridge, and then will be transmitted to a service platform and data lake. So ECMWF is building the global system based on IFS and NEMO at 4.4 kilometers. Hourly outputs and initialized so far once daily. And the on-demand one is built with three model configurations, AROM, Harmony AROM, and ALAROM, with sub-kilometer resolution capabilities, sub-hourly outputs, and also with many impact modelings, like hydrology, storm surge, air quality, renewable energy, wind and solar, thermal comfort, wildfire, and frost. So let's look a little bit on the components for the detection. It's an optimized threshold-based event detection called the OptiThread. And it's based on the input from the ECMWF ensemble. And it uses the threshold-based method calculated from climatological information. Here you can see that, for example, we use back to 20 years climatology in determining the extremeness of an event. And the output is information categorized in 1 to 5 triggering priorities based on the agreement of the severeness of the event. So far we have single variables daily with statistics of average, maximum, minimum. Talk about precipitation, total and convective, CAPE for convection detection, 2-meter temperature, 10-meter wind, speed and gust. I think we do have also 100-meter wind and gust for the wind energy. Concerning the configuration, we have an automatic system which is detecting the region with the highest impact event. And we can categorize those events based on our lookup table, which is based on our experience with the different models. You can see here the Harmony AROM, where it is applied, AROM and ALAROM. And so far, we have a duty team weekly rotating since January. And then the triggering, automatized triggering with additional information from Meteo Alarm, and where appropriate, we also use regional limited area model product. We run and maintain real-time on-demand and other components. For the first 3 months, we have produced it already around 170 sub-kilometer on-demand runs. So we do monitoring with charting and evaluation, and we involved here some of our forecasters. For example, DMI and FMI are also involved here. Here you can see the past weeks, and you can guess when we had interesting events in Europe. You can see that we did a little bit more runs during those weeks. It's mostly about floodings, storm, and convections, some of them also on during summer heat waves, wildfire, but most of them run with a grid point at 500 meter. We do also 750, and nowadays we are looking even, depending on the events, but we're also running larger domain with 1 kilometer, even 2 kilometer. So as I said, it's a combination of automatic and manual triggering. Talking about the impact sectors, renewable energy, that is incorporated in the model. So we have wind and solar based on parameterization and post-processing. Concerning the flood, we do have already in the workflow now the eHype, which is pan-European, can run over pan-European domain, but we still do a zoom inside the on-demand domain. And that is supported by 9 pilot applications distributed in Europe. Here, for example, you can see the one used in Slovakia. And regarding the air quality, we added one more chemistry model in the system, and now we have 7. And the idea is to have an uncertainty quantification based on multimodal approach. We have also a thermal comfort. In phase 1, we looked at different indices, and now we found out that UTCI is one of quite nice one, and providing quite accurate information. So we'll use that. Storm surge, we have 2 pilot areas, Adriatic and Baltic. While and we do have 2 applications. So the Hydra is a machine learning based algorithm, will be able to, as a second detection scheme here for the sea level height. And also it is also used as a prediction system in Adriatic. But in Baltic, we do have NEMO, which is coupled with the sub-kilometer on-demand system to do update and forecast of the sea level height. We do have also FROST for agriculture, which is developed by our Czech colleagues. What is making the on-demand a little bit different from the fixed domains? Here we are showing prediction of a flooding case over Denmark, running the same model with the same domain, but the domains are shifted a little bit, slightly. By doing that, we got different predictions, and our colleagues claim that the one in the sea at your right-hand side is the most closest to the observation. So the decision on which domain size and where it should be located matter. We looked at added value of the digital twin system, both global and on demand during phase 1, and we still continue doing that back in looking at historical events. Now we are going more to real time. Here, as an example, back to the Boris case, which is thanks to our colleagues, at Geosphere Austria. I don't know how many of you familiar with this, what we call panelification verification method. Okay, so it's a very nice intercomparison verification platform using verifying field, which is here. In this case, it was an Inca analysis. And then all the forecasts, all the available predictions are put together. And then we look at one domain, which is pointed here with the black rectangle. And then we look the performance of each of the models, and the system itself is categorizing all of this performance by the fraction score. So here you can see that the two global models, so the blue one is the operational one, and the yellowish is, or orange is the global digital twin. And then you have here all the regional systems. So the green one is the AROM Austria, and the red one is a pre-operational ensemble they are developing at Austria, and those were with Circle are the digital twins run on demand with different placements of the domain and focusing on different countries, as you can see here. So we can say that the digital twins, they are performing very similar to the operational systems, and some of them even performing even better than the existing local one. So they can be really complement the existing local systems. Another example of the Storm Pia, where you can see the operational IFS, digital twin, global digital twin, free AROM and Harmony AROM. And here you can see the verifying values of wind gust. Well, you know, verification is, you can point to always to something that to show that one of them is better. But I leave that fantasy to you. But the good thing is that they are really, you know, at least the digital twins, they are very close to the truth, I would say. Another example, I think I will skip this one in, to gain a little bit time. Then at Met Norway, we are getting these the on-demand runs into our visualization tool. Nowadays, this is a case a few days ago, and on Monday we got another one in North Norway, and we will look at that. And here we have these operational maps, and this is Norge, it's a precipitation analysis, and here is the digital twin we're using Harmony AROM at 500 meters. Yeah, okay. Again, we can say that the two NWP models, they're a little bit overestimating the precipitation, but for the prediction point of view, I think they are performing quite nicely. And here you can see even more about the observations that were used in the verifying analysis, if you want. Another development going on at ICMWF, it started already in phase 1. Attempting to have an ensemble, few member though, but with high resolution. Here you can see the difference from going from 9 to 4.4, and if you compare to the verify minimum core pressure at sea level with this tropical cyclone, you can see that these going to the high resolution is already adding value. And some development in the convection scheme providing a reduction of cloud-based mass flux already adding quite nice performance. So far so good. And then we started in phase 2 to also work on ensemble model systems. This is a physical-based one, and Ingrid is leading this. And we start again with very few members, 750 meters. This is a week period verification. They are focusing on boundary nesting and model uncertainty description so far, and trying to compare this with post-processing and machine learning based. We will have that later. But we can already compare that already with the operational systems, which is done here in right-hand side. This is a case of heavy precipitation over Sweden. This is the truth, and this is your operational forecast, and control missed it. But if we look carefully, then we can still find some member which could make it. So far so good. This is just activity just started. So yeah, we will see where we can end up. Yeah. Concluding. So, concerning the global system, we can say that clear added value we've observed it in certain extreme events when increasing the resolution. We saw that, and intensification of tropical cyclone and Medican, for example, orographic precipitation or other surface variables in complex orographic areas. But less clear added value, I think it's valid also for our regional one, was observed a surface variable and local convection for flat area. Maybe we were concentrating too much to complex areas. And concerning the global regional systems, the accord NWP sub-kilometer, so going from 22.5 kilometers to 500 meters, showed added value on specific cases, but we need to be further, this needs to be further explored. And the benefit of the accord compared to the 4.4 kilometer is observed in various high impact events. But as I said, we continued evaluation to really have a clear conclusions. We think that the lack of ensemble and the specific data simulation at sub-kilometer scale may partly explain the absence of added value for certain cases. And that's why I said we are working on uncertainty quantification and also statistical post-processing. And this including, by the way, I didn't talk about it because I don't have time, but we are also working with data-driven system, which was shown by Jorn a few days ago. So yes, that's it, and thank you very much.
Thank you very much, Roger, for this very interesting talk. Questions to Roger? Yes.
Thanks, Roger, for your talk. I am curious about the triggering method OptiFresh. I can see that it is based on the IFS ensemble, and your tool seems to be based on probability threshold and so on. There are dedicated tools in the IFS ensemble in order to detect potential extreme forecast. Should I conclude that extreme forecast indexes are not used to detect extreme forecast?
That's true, but this is the first attempt. As I said, we are developing this. All those will be definitely incorporated. For example, for fire, wildfire, for example, the indices will be used definitely. But that will come later.
Other questions for Roger? I have one maybe concerning the on duty. Where? Oh,
Thank you. At the convective scale, there are different schools of thought, but normally many people say there are no fixed threshold for convective initiation, like cape, shear, and so on. So at the regional or local level, when you go further, are you considering to have a similar triggering at an even smaller scale so that you can issue warnings or have extra runs at the very hectometer scale?
This is really very, very good question, and thanks for that. And I'm looking to some of the posters here that can be also potentially added in our system. As I said, this is really the first LIGO we had based on very low resolution ensemble system. We know the consequences of that. We will try to also see if we can use, for example, regional ensembles. But definitely, as I said, for example, for solar energy, we have a Nowcasting system that is taking into account, I hope, this really this small scales. And that is up to from 1 hour to 3 to 6 hours.
Other questions or comments?
You can ask yours.
Thanks. So this, concerning the on-duty aspect, so how do you see, because of course this is, we are at the second phase of this project, how do you see the next steps of this on-duty
Well,
applications?
for the time being, we do it in work time, no weekend. Weekend, we just leave it going. And we take it on Monday. Monday, we have a little bit longer because we look at what will happen on weekend. But I do believe that once, maybe I can go a little bit further. So, what is it? This activation. So we look forward by the end of phase 2 to have a kind of automated domain definition, and in that case, still needs all of these duty forecasters because sometimes model is just crashing. But yeah, I believe that that solution will be found for the future, and we hope that we will have phase 3 anyway. So that to think about what happened after phase 3, that is we leave that a little bit for a later decision. Yes.
Okay. Last question.
Thanks. This may be a stupid question, but I'm going to ask it anyway. They say there's no such thing as stupid questions, but we'll see. So when you run the on-demand model, is it run in real time ahead of an event, or are you running it after an event for post-analysis?
That's a very good question. Thanks for asking that, because so what we are doing now, as I say, that we are really putting the different Legos and including, that's a part of the, when I show the workflow, we were talking about the system that should run on Euro HPC, but for the time being it is run on Ethos. The reason for that is simply that the Lumi is not really ready to be used for operational or pre-operational application. The other thing is, to answer properly your question, the global digital twin is based on the analysis from the operational one. They don't do data simulation locally. So that can have already consequences in timeliness. And so far, with all of this complex situation, I cannot tell you exactly what is the delay, but we try. All of this triggering are in real time. So we know what will happen tomorrow. We know where we need to run the domain tomorrow. But will that in real time be production? I cannot tell you that is today that can be possible. It can be really very delayed due to all of these technical issues. Okay. But we aim at.
Okay, thank you very much for this very nice talk, and we have to move on. Jonathan. Okay, so next talk by Jonathan de Meyer concerning the past and current and future activities on statistical post-processing in the context of UMetNet. Please.
How do you go full screen on your computer?
I don't know.
F5, mais ça marche pas.
This is not this one.
Non. Tu dois peut-être aller dans le menu.
I don't know. Je sais pas. Ah, attends. Tu as essayé?
Does someone know the shortcut on Windows to go full screen? Control L. Okay.
Oh. No screen. Ah.
Thanks. I'm a Linux user. I don't know Windows. Sorry. So yeah. Good morning, everyone. So I'm Jonathan de Meyer. I'm co-leading with Stefan Van Itzem the PP module, and I'm going to talk today about. Well, yesterday we had the discussion yesterday afternoon, and we mainly talked about the current and future plan. So today I decided to focus a bit more my talk on the past. Voilà. So the PP module is dedicated to the study and of post-processing method for weather forecast, but in a collaborative manner across different institutions and also with academia. So we are a bit more, let's say, an open work flow than maybe the other MetNet package, in the sense that we also include academia, because we, at the present phase, this is very focused on research. So then the idea, during the first phase of this project, the idea was to be able, because there were many different methods published since long time, and currently the pace is increasing. There are new methods every month, or every new papers. And the problem is that in those studies in general, people compare their results in a certain specific setup with a certain specific data set, and they compare 2 or 3 methods to see the advantage of new ideas or new methods. But then the question remains, how does it compare across a whole range of methods? And this was a kind of question that was the PP module first wanted to address. And I think that for this, that was the case for the past phase, but this is still the main question for the current phases. So here you have a lot of methods, different post-processing methods, and this figure comes from a paper where all those methods were a bit ranked in a very rough way across 2 axes. So from this is very qualitative, of course, from less flexible to more flexible, and also from how it is easy to implement to harder to implement. A method which is flexible doesn't mean that it's simple to implement, because implementation depends on many different factors, like access to data and things like that. Here, flexibility means more, I think, the ability to deal with different situations, different variables to post-process and so on. And so this study was published in BAMS at the beginning of the phase 1 of this module. And then the idea was to, here you have a qualitative assessment, but the idea was to go to a more quantitative assessment of the performance of those different methods. So for that, as I said, all those papers in general, they use different data. And the idea, if you want to make a fair comparison here, is that as input, we use the same data set. And so the idea was to create a common data set that we could use as a baseline to compare the methods. And this data set was published in ESSD in 2023. So that was the last publication, I think, of the phase 1. And this is the domain of this data set. We choose a restricted domain to avoid having too much data to handle. And you have gridded data, but also station data, and you see the blue dots are the station. And here you have a sample of all the variables that are available, but actually you have roughly 40 variables available in the forecast of this data set. one thing also that is nice with this data set is that we automatically paired the forecast and the observation. So the user do not need actually to find, this is a huge part of the post-processing task when you do it, is to find, well, the forecast, you have them from NWP, but then you need to find good observation to verify and to train also your algorithm. So, yeah, this is more like a recap slide of what I've just said. I'm gonna skip it. So the data set has this. This is a bit the characteristic of this data set. So it is IFS forecast mainly with ensemble forecast, but also the deterministic high resolution one. We have a 2 years span period with that correspond one forecast a day. We use only the midnight analysis, and that's 730 forecast. But then we also provide the reforecast, which goes 20 years in the past with the current model, but with the past analysis. And that's an additional 20 times 209 forecast that can be used to train, actually. So in general, reforecasts are used to train the post-processing model, and then you post-process the forecast themselves for verification. And that's what we did in this paper also, I'm going to explain. You have surface and pressure level data, and as I said, roughly 40 parameters. And for the observations, for the gridded observation, we use the ERA5 data. So the resolution of the data set is quite low because it's 25 kilometers. But that was a first step, actually. And if you were yesterday in the PP module discussion, we are going to complement this data set now with more high resolution forecast and observation. But as a first test for this first phase, this was enough to have this 25 kilometer resolution to start the benchmarks. And we have also station, which are, again, it's the blue dots here, from Benelux, Germany, France, and Austria and Switzerland. And all the forecasts are matched to observation in the station. That means that we have observation back to 20 years in the past for most of the station. For some station, it's a bit more sparse, but we tried as much as possible to find all the data to fit the forecast to the observation, to the station. How much time? 5 minutes? Okay, I'm fine. Yeah, and for the access to the data, this was very important that this data set become open and accessible not only to NMHS but also to academia, because the idea was to foster the collaboration across academia, across the community in general. And because many of this is to compare also new methods coming every month in the literature. So you have to open this effort to the whole community. You cannot only focus on NMHS here for this present phase and this present module. And for this, we teamed up with ECMWF, and we developed a Climate Lab module, plugin. Climate Lab is a code based by ECMWF, which allow to access different data sets in a seamless fashion, I would say. And but all this data needs to be open. But also, to be sure, in addition, we put the data on Zenodo. And so the gridded and station data are both available. So again, all the station data and all the gridded and forecast data are open and licensed. So this was okay. Now, if you use the Climate Lab plugin to access the data, it's a Python plugin, then you get the data in a specific format, because behind the data set is stored in a ZAR format. which allow you to access it quite straightforwardly. If you are using Python, this is easy through the Xarray library, but you have also a library in R and in Julia to load the data. And the data, then you benefit from all the nice feature of the Xarray object. For example, in Python, you can slice in the dataset quite easily. And this was important because, for example, the machine learning community use more and more this kind of data structure. And they are mainly using Python also. So this was important to allow, because machine learning, of course, is used more and more in post-processing. So that was important. You have to remember that when we designed the dataset, it was 2019. So it was, at that time, it was not clear which format and which language will dominate. But I think we made the right choice with ZAR and Python. Of course, you can use also Julia and the other language, but let's say this was done initially with Python in mind. And then, so this is, for example, the structure of a forecast dataset, a part of the dataset of the forecast. But then you can also request the observation, and you get the data in a similar format. And what's important is that all the observation and forecast data are already time aligned. So you don't need to think about, I need to align the data of the forecast and the data of the observation. So that was important also to have really a quick access to the data, and that people could focus more on developing their methods and less focus on the data, which is usually is the other way around. People spend a lot of time on the data and actually less time on the methods. In general, I think. Maybe we can make a poll about this, but I think, all right. This is, for example, an example of a gridded forecast for total precipitation. This is just an example, but here, for example, you have a forecast over the domain gridded. So it's 25 kilometers, observation area 5. And here, for example, you have the forecast. Here you have the observation. And I think that below, this is actually a reforecast at a different time. But so that's how it looks when you get the data out. Then we publish this data set in ESSD. But the idea was we cannot only publish the data, we also need to show a bit how to use it and what you can do with it. So we decided, within the PP module, with all the participants, to make a simple post-processing benchmark experiment. And we designed it as simple as it was possible. So we post-process temperature, 2-meter temperature with as target. And the predictor, the only predictor we used was the 2-meter temperature itself. And we also decided to focus on a station and not on the grid. And the period for the training that we used was 2017, 2018. That was the reforecast. And we used also the 2017, 2018 forecast as verification, so as test. And the score we consider were the usual one, I would say the most standard one, so CRPS, bias, RMSE, and so on. And again, the verification data were on the synoptic station. So we also had different team. We tried to work in team to a bit emulate how it will look to have a bigger effort later. That would be actually in phase 2. I spoke about that yesterday during the discussion. One was the dataset preparation team, which actually the dataset was already prepared, so that was mainly me, I think. I should not have written that. Then the selection and application team, which selected the method and applied them. And then the verification team, which was led by Christina, who's here. And this is the first result we got with the benchmark. With questions? Okay, I'm gonna really finish now. So this is the result we got. So you can I'm going to go faster now. So, but you see all the different methods. We even had some neural network method, even if it was very simple post-processing task. And you see that maybe the main things I will show here is that in black, this is the whole IFS forecast. And here you see the pack of post-processing methods. The neural network one is the best one. It's the yellow one. But actually, we also realized that there was a big difference with this one, is that all the other post-process lead time bears lead time, while the yellow one takes all the lead time as input for every target lead time. So this method was actually developed by Peter, which is, I don't know if you're gonna talk about this today, but okay, later. I know you talk at some point, but okay. So voila. So the dataset has some later impact because people started to use it, and so we were quite happy that it is being now useful to the community to actually compare and actually some because we put a lot of data in it, but it was not sure how it will be used. And for example, Sandor Baran, they started to use it to post-process visibility, which was not really intended in the first place, but we put the visibility data because they were available, and he actually was very useful to him because he was looking into that at this moment. So this is a slide about the next phase, but I spoke about this in the discussion, so I'm going to go fast now. And we have a new website that you can visit if you want to keep up to date about the status of the benchmark. So thank you.
Thank you, Jonathan, for the presentation. Questions for Jonathan? I don't have any, so.
Okay, thank you very much, Jonathan. So from your presentation, I have the impression that really the big part is about data curation, right? This is also, I mean, from what you did, but also the way people look at this activity. They use, I mean, this UPP bench to get data and to eventually sometime invent their own task and try to use the data to see how it works. So is it, I mean, in terms of future plan, is it the way you see it as well? I mean, that the biggest part will be about data curation and eventually the task definition should be loose.
Thank you for this question. It's a good one. So as I said, preparing the data is a huge part of the post-processing activity, I think. So that's not a surprise. And somehow I focus a lot on this myself, which then when I make the slides, I think is being showed somehow. But in the end, it should not be the case, which means that I think that after this next version of the dataset, I think I'm going to stop myself working on the data and focus more on managing the activities and the other goals, which means that it looks like that now, but I don't think that at the end of phase 2 it will look like that anymore, and it should not, because it's not a module solely about dataset. You are right. So I know that it looks like that for the moment, but I hope it will not look like that at the end of phase 2. Maybe now we are starting phase 2, and because of that, the first thing you start to do is collecting new data for the new goal. But I think that at the end of phase 2, dataset will be, I hope, fixed for once, and we are not going to look into data issue anymore. We are more focusing on the methods, more focusing on onboarding people with tutorials, because that's also a goal of the PP module, is to help an MHS onboard people and also look into, for example, research to operation. I didn't speak about that, but a huge importance for the NMHS, I think, now is research to operation, and we want to look into that. So yeah, that's, I know it looks a bit like that. It's a bit a dataset module, but I hope that in the end there will be many other aspects and it will not be the case anymore. Thanks.
Thank you, Jonathan. Other questions? If not, maybe we can move on to the next talk by Tobias. And wait, this is, yes, it's there, look. So, Control L. So yes, so let's move to the next talk, and with presented by Tobias Bigert, right? The right way to say it?
Yeah.
Probabilistic benchmark and post-processing for data-driven weather forecasting. Please go ahead.
Thank you. I'm Tobias Biegert. I'm a PhD student at Karlsruhe Institute of Technology in Sebastian's group, and I will today present you probabilistic benchmarks for post-processing and post-processing for data-driven weather forecasting. So, as you're probably all aware, there's a big surge in data-driven weather prediction that is transforming the weather prediction landscape, and recent models are able to outperform numerical weather prediction models in certain deterministic metrics, and as an additional advantage, they also offer substantially faster forecast generation. Despite these advancements, though, the models mainly focus on deterministic outputs. And this, of course, is a disadvantage because the forecasts lack the information that is important for decision-making and risk assessment. And what we are looking at is we wanted to look at if we can use post-processing techniques to generate probabilistic forecasts from the deterministic model outputs in order to compare then the post-processed data-driven and NWP models, and also just offer probabilistic benchmarks for possible future data-driven models that will most likely inherently produce probabilistic forecasts. For data, we used the WeatherBench 2 data sets. So that's a collection of a lot of data-driven and NWP data sets. We focused on Pangu weather and GraphCast as the ML data, and the IFS high-resolution forecasts as the deterministic NWP model, and then the IFS ensemble as the probabilistic baseline. We focused on these because these were the only ones within WeatherBench 2 that offer data outside of the evaluation period of 2020, which was needed in order to train our post-processing methods. We did it for all the lead times from 6 hours to 10 days in 6-hour increments, and then on 2 different resolutions, one pretty coarse resolution of 5.625 degrees and then 1.5 degree global grid. Yeah, as the observation data, we use error 5 for Pangu weather and GraphCast, and then the IFS analysis for the IFS models. And we focus on 8 target variables, which are also the headline scores defined within WeatherBench 2. This is 2-meter temperature, mean sea level pressure, 10-meter wind speed, total precipitation at 24 hours, geopotential height at 500 hectopascal, specific humidity at 700 hectopascal, and then at 800 hectopascal temperature and wind speed. Now let's look at the different post-processing methods we used. So first, a relatively simple method, a non-parametric method, we call error ensemble. Here we just compute errors during the training window, and we maintain the spatio-temporal structure. So we just use for one initialization time the entire forecast of the entire deterministic forecast, and subtract the observation or the reanalysis. And yeah, to then generate the error ensemble, we sample a number of these training errors and add them to a deterministic forecast during the evaluation time. We can do this, for example, for 50 members, or for 50 past errors, we sample them, add each of them to the deterministic forecast, and thereby generate a 50-member ensemble. Then the next method is model output statistics, which probably everyone is relatively familiar with. just very shortly, it's parametric approach. We have to define the predictive distribution family we want to use for the variables. Here we use normal distribution for the temperature variables and mean sea level pressure and geopotential height, and truncated logistic distribution for the wind speed variables and the specific humidity. Then we link the parameters of these predictive distributions to the model outputs, here x, using these two link functions, and then optimize or estimate them by optimizing CRPS over the training set. We have two different model output statistics variants here, one global and one local. So for the global one, the parameters A, B, C, and D would be the same for the entire grid. And for the local one, we do it for each grid cell separately. Yeah, we do it different parameters or different optimization for each lead time. And then a bit newer method, EasyUQ, which is a variant of isotonic distributional regression. Here we basically can produce statistical distributions from model outcome pairs, and we just need one key assumption for this, the isotonicity assumption. So we assume that if the model output is greater than another model output, then its respective forecast distribution has to be in a higher stochastic order. And then this can be translated into a non-parametric optimization problem, and we can then obtain the predictive distributions via this formula. One very attractive feature of this method is that it doesn't require any tuning parameters, so we basically can just use it out of the box. If we now look at one example prediction here from Pangu weather for temperature at 850 hectopascal for a 3-day lead time, in brown, the deterministic forecast, and then we generate these 4 different probabilistic distributions from it. We can see the parametric approaches of the local and global model output statistics in green and orange, and then the empirical distribution of the error ensemble in blue, and also the discrete stepwise distribution that is produced by the EasyUQ method. Now we looked at many metrics to look at the results. So for example, we derived the expected value from the predictive distributions and applied bias and RMSE. We also, of course, looked at CRPS and then also assessed the calibration using spread skill ratio and PIT histograms. But for this presentation, we're just going to focus on CRPS and only for the 10-meter wind speed and the temperature at 850 hectopascal for the 1.5 degree grid, just to stay inside the time. So if we compare the methods, here on the left side for 10-meter wind speed and on the right side for the temperature variable. So in red here we both see the GraphCast deterministic forecasts in terms of CRPS, which in that case then just is the mean absolute error. And in blue, the probabilistic baseline of the IFS ensemble. And now with post-processing, we can see, for example, for the temperature that we can beat the baseline for up to 5 days. What we can also see is that local model output statistics generally performs better than the global one, which I think is not very surprising. And also the error ensemble does not work quite as well, typically as local MOS and EasyUQ. Similar story for the IFS high resolution model if we post-process it. But here we can see we do not really beat the IFS ensemble baseline in terms of CRPS. Now here we get a better overview over all the results for these two variables. So at the top, or on the left side, we see again 10-meter wind speed, on the right the temperature at 850 hectopascal. In the topmost row, there's the baseline, the IFS ensemble, and then the three blocks are for each of the deterministic models. And then again, in each of those blocks, the topmost row is the deterministic evaluate, or the CRPS of the deterministic forecasts. And then below that, with post-processing. What we can clearly see, we cannot beat the IFS ensemble on longer lead times, but for shorter lead times, especially at the 850 hectopascal temperature, we can improve on, improve very much the probabilistic predictions and also beat the baseline for up to 5 days, for example, for GraphCast. We can also see here that GraphCast in general produces the best probabilistic forecasts. Regarding training time, here we can see that EasyUQ generally took the longest to train. We did this on the Google Cloud platform using some Google Cloud credits we got as part of a grant from Google Research. This was deployed in a distributed fashion using Apache Beam, which also uses the task structure of SAR datasets. Now, if we look for the same method, so the same post-processing method applied, in this case error ensemble, we can see here the continuous rank probability skill score compared to the IFS ensemble. On the left side, we can see for wind speed, for 10-meter wind speed, we basically can't beat the IFS ensemble here using the error ensemble post-processing method, except for very short lead times. But for the temperature at 850 hectopascal, especially for the GraphCast model outputs, we can significantly improve for lead times of up to 5 days. Here's the same with the local MOS post-processing. We can see in general it works better than the error ensemble, and also here we can improve using the Pango weather predictions. What can also be seen relatively clearly here is that GraphCast works the best, then Pango weather, and using the probabilistic predictions generated with the IFS high resolution outputs do not work as well. Here we can also look at spatial CRPSS. This is for a 3-day lead time post-processed with EasyUQ. And then in the top row, you can see 10-meter wind speed, bottom row, temperature, and then on the left for Pango weather, then GraphCast, and on the right, the high-resolution IFS. Now, as a summary, so in general, EasyUQ and the local MOS perform best and can achieve improvements over the IFS ensemble for lead times of up to 6 days. For certain variables, and then the GraphCast-based predictions outperform the Pango weather and the IFS high-resolution based ones. As a general observation, if we look at the relationship of the deterministic evaluation, so let's say we look at temperature at 850 hectopascal, and we compare the RMSE of GraphCast versus the RMSE of the IFS mean, then we can see a very similar pattern as we then see after post-processing using CRPS. So basically, in the deterministic evaluation, a GraphCast can also improve on the IFS ensemble mean for up to 5 to 6 days for temperature, for example, and then we can transfer this advantage into the probabilistic setting using these post-processing methods. Now, as next steps, we want to implement more complex post-processing methods. So, for example, distributional regression networks. We already did some of that for the temperature variables. And we also want to apply these post-processing methods, the ones where it makes sense, to the IFS ensemble, and also possibly data-driven ensembles if those data sets become available within WeatherBench 2. So for example, neural GCM. And we want to incorporate this code and this prediction data sets into WeatherBench 2. Thank you for your attention. I'm happy to take any questions.
Thank you very much for this very interesting presentation, and to see that we also need post-processing for these models, this type of models. Questions? Okay.
Thanks for this very interesting talk. You were mentioning risk-based applications in the beginning, and you were showing mostly sort of average scores. Are you planning to also focus more on the sort of climatological tail of the distribution, extreme events, well, rarer events, to add a bit to the relevance? And maybe as a related question, do you think the comparatively low resolution of your evaluation has an impact on the relative skill of, say, high-res versus Pangu weather?
Yes, for the first question, we did not look at extreme events yet, but that would definitely be an interesting investigation. For the second question, so we didn't do it at higher resolution than 1.5 degrees because it's global and that would be extremely compute intensive. So we did it for the 5.625 degree, which is very low resolution, but so we can see there it's a little, so we get a little bit more improvement for the lower resolution than the 1.5 degree results. So it is definitely possible then if we go to higher resolutions that the results or the gains we get through the post-processing will diminish a bit more, but the ranking basically was the same. So GraphCast was still significantly better than the IFS high-resolution model.
Yes.
Thank you for the nice talk. I have a question about, so maybe it's an outlier for your talk, but I'm still curious. So one sees in the literature that there are methods popping up proposing data-driven approaches to provide inherently determined probabilistic forecasts. And I wanted to ask if you compared your methods with those, or do you plan to compare your methods with those?
Yeah, so we definitely plan to compare them. And it would also be very interesting to also apply these methods to some data-driven ensembles, for example. But they are not available yet in WeatherBench 2, especially outside of the 2020 training window and test window. But yeah, of course, this was also part of the intention here to basically show how much CRP or how good you can get with these data-driven models using relatively simple post-processing methods in order to produce probabilistic forecasts. And then data-driven models that produce inherently probabilistic forecasts, like for example GenCast, can be compared to those and should definitely beat them in order to justify their much higher inference time.
Yeah. Yes. Last question.
Also from my side, thanks for the talk. It was very interesting, but it was a lot to take in, so I probably will approach you later. But a burning question now is, and I may be wrong, but I'm more experienced with the 2-meter temperature, and that's the question a little bit more related to that. But I assume the 850 hectopascal temperature is also under-dispersive in the raw ECMWF ensemble, right? And just looking at the CRPS, it's difficult to see where the differences come now. But do you know from a bit histogram, for example, if the local EMOS improves that and the worst performance then comes from somewhere else? Or have you looked at that?
Yeah, so we looked at spread skill ratio and PIT histograms. And with the local model output statistics, we can get some improvement. I think I have some, at least the spread skill ratio here, for example. So if you look, for example, at temperature using EasyUQ here in violet, then we can see we can improve a little bit on the IFS ensemble spread scale ratio. But all of the methods are somewhat underdispersed here for temperature, and yeah, global MOS is very underdispersed.
Thanks.
So thank you very much, Tobias. And let's move on to the next talk by Christian. I don't know how to do that.
Slideshow, I think it's.
Is it there?
Or is this one?
Diaporama.
Yeah.
Oh, wow. Amazing.
Thanks a lot. It's loading, right?
Yeah. Loading. Uploading what? I don't know.
Ah,
Oh, yeah,
there we
it's
are.
good. Yeah.
Okay, thanks a lot for inviting us and organizing this beautiful conference, and thanks a lot also for you to be here and listening. This is a research group made by people working on the climate section and in the development of numerical weather prediction. So we have a foot in the past and one in the future, so to say. And I work in the climate division, so I'm more interested in the past, right? So now if I go down, or left, all right. I'm gonna talk to you about this Meta-Nordic dataset, which comes in different, it's a collection of datasets. We have a real-time stream, which is comprise the analysis and the forecast for different variables. And we have also a long-term consistent stream, which is very close to the Meta-Nordic analysis, but it takes a reanalysis as the input instead of the numerical weather prediction. So these are all the variables that we are post-processing: temperature, precipitation, wind, also relative humidity, radiation, and pressure. But in this talk, I'm going to focus on the analysis of temperature and precipitation. And the other post-processing for the other variables is a bit simpler because at the moment we are focusing on these two. And we have chosen these variables because are the most important for basically the hydrologists and everyone that is interested in the water cycle at the surface of the Earth. And yes, so temperature and precipitation will be the main topic in the analysis. In a sense, if I understand well, this is a kind of a training data set for this community or a validation data set, if you want. We are doing this operationally since 2018, so everything that I'm going to tell you is operational. And we use observation that are not using the model. Then we use the model output, the numerical weather prediction in this case, or a reanalysis in the other case. And we try to do a combination. And our mantra for this product is to use all the available observation at any given time and adjust the model realistically to stay accurately aligned with the observation. That's not an obvious choice, because if you have other application in mind, if you want to compute temporal trends and do climate stuff, if you use all the observation, you were likely going to mess up the trend. So other application may have, it will be convenient to do different choices. But for automatic weather prediction or for civil protection, these choices are the one that the customer wants. So the numerical weather prediction, this is the domain, and let's say the numerical weather prediction we use is exactly the one that is operational. During different times, you have different numerical weather prediction models, but the users usually want something which is as simple as possible. So a benefit of this post-processing is also that they can get the same file independently from the model which was available at the time. So that's also something useful. Of course, now we have delivering an ensemble. For the past, we have only a deterministic model because it was a deterministic numerical weather prediction. So we're going back with the archive to 2012 when the first MetaROM and Metcop was available, and then we use all the model developments. Then for the other component of this combination is the in situ observation. We are using all the available observations, so we're using one-party data, which is our own data, the WMO station. We are using also two-party data, which is the stations that are available from the other governmental institution in Scandinavia. And then we are using also opportunistic measurement from citizens. Of course, the sensors are really different. You can see most of the opportunistic measurement comes from Netatmo, but we are also using other 5 or 6 providers. As you can see, the instruments are rather different, but the strength is in the number. It's actually redundancy that gives us the possibility to use this data source. We have so many that we can, it's very unlikely that 100 people that live nearby to each other, they all make the same mistakes in placing the station, right? You have a larger spread, but on average, you can think that the errors are independent, so you can get something which is useful for you. I can show you a picture like this to see that the strength is not only in the number, but they're actually measuring something which is related to the weather, right? Because you can see this was a thunderstorm, and you can probably recognize Oslo. We are somewhere in the Oslo. We are kind of here now. Yeah, somewhere here. This is the Oslo region. This is the peninsula. And there was a thunderstorm going from north to south. This is 10-minute animation. And you can see that we were able to discriminate between part of the city that were hit by the thunderstorm and part of the city that were not. This image was also taken by the national newspaper, so it's easy to convey the information. But you can also see that some of the stations are wrong because they're measuring no precipitation at all. So it's our duty to take out the stations that are wrong, and I think Amélie has described a bit what we do with quality control yesterday. We are also comparing this data source with other different data sources like radar data, and they usually agree quite a lot. If you want to know more about the radar data in Norway, we have the guru of the radar network sitting there, Christopher Edo, so you can talk with him. There is also a poster outside. And here, for instance, we are using the radar. There is a thunderstorm or an event which is going from south to north. And you can see that we have a lot of observations that are seeing the same weather, and they agree quite well. But again, there are observations that are wrong. So it's quite clear to see that here you have a 0 millimeter that stays always 0. So it's a tricky data source, but there is information there. What is the method that we are using for doing this post-processing? Is a statistical inverse problem theory. We call it ANSI because it's an ensemble-based statistical interpolation, but it's very much taken by the work from Geir Evensen and is ensemble of the interpolation. So the method is the schematic here can give you an idea. So we have the truth, which we don't know, but we assume that the observations stay very close to the truth, right? So the blue points here are the observation of any variable. And then we have an uncertainty, which is this circle around the observation. And this is the ensemble with all of its uncertainty. The ensemble is less precise than the observations. So we do this post-processing with ANSI, and we end up in having an analysis which usually stays between the observation and the model background. And basically, we have all the tools to tune the uncertainty and the analysis as much as we want. So it's really up to us to do a good job because we can really obtain everything we want. And the method is described here. It's a classical, I will go a little bit more on the different blocks, but it's very much close to Kriging, or you can write any spatial analysis method in this way. If you want splines, it's not too different. And everything that I'm talking is also available in the gridded post processor. It's a GitHub repository. We have also a nice wiki, so if you go there, you can find a lot of information and examples if you want to give it a try. And we are kind of using inverse problem theory to solve the spatial analysis problem. So this is just a few slides to show you an example and to explain the method at the same time. This is a valley in Norway, but could be in the Alps, I mean. This is the valley floor, and this is the model plus all the observation. So the model is telling this story. The model knows that usually temperature diminish with the elevation, right? It's a common experience. So the valley floor is warmer and the mountain top are colder. So that's what the model is predicting for the future. But the observation is telling us a different story, because if you look at the analysis, the observation are actually colder on the valley floor, and we have a lot of them. So we can really see the spatial structure of the cold pool. And the mountain top here, it's warmer than the valley floor most of the time. While here we don't know nothing, basically. But here we know that the mountain tops are warmer. So there is a temperature inversion here. And the analysis is actually colder here than the background, as you can see, because the background is warmer. So the model was not making a good job for this specific hour. And in Norway, the inversion can be quite strong. So your verification can go wrong by 10, 15 degrees if the inversion is not taken in a good way. And of course, the observation are colder than the model background. So we are using the nearby observation to adjust the background. And everything that I told you so far is there's not choice from us. We get the model, we get the observation. So basically, it's only data management. But the real magic thing where we have to put our knowledge is on defining the weights. And the weights comes from the way we define the statistic correlations. We can do it in a very easy, let's say, way based only on geographical parameters. So we know that the far away you go from a point, the less is the correlation with everything that is going on in that point. And the same thing can happen in the vertical. So we can define this type of, and then you are basically doing kriging or optimal interpolation with static correlations. Or you can use an ensemble-based, you can use the ensemble and the geographical information to define the weights, such that you have a kind of a weather-dependent correlation that takes into account the specific of the weather for that hour. Then you can apply some localization techniques to get your correlation, and that's what we do. Now, if I go to the next slide, just to tell you to share one thought that could be interesting, maybe is also a matter of discussion. Let's say the ensemble in the spatial analysis the meaning of the ensemble is different from the meaning of the ensemble in the forecast. Because let's say you have an ensemble mean, this blob here is the ensemble mean of a precipitation event. And you have the ensemble mean in a data dense region, and you have the same ensemble mean with this precipitation event in a data void region, right? I apply my own spatial analysis and I get the same. I can even get exactly the same ensemble in the two different regions. So here, I can really have 30 numbers that are the same here than here. And then I can give this to you to do your verification, right? But actually, the meaning of the ensemble is really different in these two places. Because when I have a lot of stations, I'm giving you the representativity error, right? So what I'm telling to you is the variability of the observation in a region is that and that. But if I don't have any observation at all, what I'm giving you is the prediction uncertainty. So it's a really different information. And now I can go with some results. And temperature, and here it's just 2 hours for one specific day. In the top row, you see that 9 UTC, and so this is basically morning, middle of the day, and this is during the night. And this is the analysis ensemble mean minus the background, so analysis minus, that's the correction we do to the model. And you can see that it's different from different hours of the day, and you can clearly see the valleys. And the spatial structure is so well defined because we have so many observations that we can really play with the different gradients. But this map, here we have the problem that I was mentioning before. The ensemble standard deviation in Oslo is always very small because there is observational uncertainty, is representativeness error. While the ensemble standard deviation in the mountains is usually higher because that's prediction uncertainty. It depends also the lead time of the model that we are using. So it's a tricky field to take into account. But anyway, it's the best information we can give you about the uncertainty because where we don't know nothing is actually the model that can give us some information. Now, this is some verification. It's the percentage of large forecast errors. And here you have the lead time. The red line is basically the statistics of the NWP in 2020, so it's not really updated. It was from a paper in 2020. And this is the NWP plus Netatmo, the blue line. I'm actually interested only in what's happening here because I'm working with climate, so for me, tomorrow's weather is good because it's going to become the past, so that's why I'm interested in it. But the people that look in the lead time, they also show that they benefit of this 65% improvement. We are kind of keeping it. So even with some simple post-processing techniques like this, a good analysis can give you a benefit in the post-processing. Thank you. Now I'm going with precipitation. Precipitation, we are doing this for precipitation. This is the analysis plus the observations. And this is exactly the case that Roger was showing before, the ANS extreme event in August, the one with the caravan going under the bridge and so on. And you can see this is one specific hour. That's what we are doing today. Today we are good, but this is not an independent evaluation, but we are kind of smoothing the extremes. And we have a lot of places where maybe we should not have zero, but something more. So the new method that we are implementing is still new ANSI. It's a bit better because we are not smoothing the extreme that much. You see, it's more, the field is more variable. And all that we are doing is using also a data transformation because before using this ANSI. This data transformation is a simple box-Cox transformation with, basically we take the square root and we do some manipulation. But that is actually creating some problems. So I had to change the box-Cox with something which I call started box-Cox, and you see that the difference is it's quite a lot of difference if I use this box-Cox. If I shift the box-Cox to start not at 0 millimeter but at 1 millimeter, I improve a lot the difference between rain and no rain. And that's very good if you're, again, a climatologist, because then you have to accumulate these algae fields for 1 year, and 0.2 millimeters every hour, it becomes quite a huge number at the end. So our hydrologists, for instance, they complain that our fields are too dry. So this modification in terms of water balance can really bring benefit to the long-term data set. So this is, for instance, what happened after 20, if I do this now, this is the description of the ANS extreme weather today. This will be the next one after we implement this operationally. And for this specific day, we gain more or less 7% of precipitation more. So we increase the precipitation by 7%. And we also do evaluation based on more than 1 hour or 1 day. So this is for just to give you an idea of the ETS for over 2 years of early data. And we are able, with the new method, we increase a bit the performance of the whole method. But yeah, that's the ETS. Summary, using citizen observation operationally since 2018, and I mean, there is value there, and applying inverse probability theory for spatial analysis. Maybe the next thing will be machine learning, but yeah, it's really a revolution. Ensemble interpretation is different between different areas, and the data transformation is very important for applying this method. So the box-Cox is good to spend some time in the data transformation. Sometimes you do it very quickly, but sometimes you can benefit from from spending some time on that. Yeah, that's it for me.
Thank you very much, Christian. Very interesting talk. Questions? Yes.
So I have actually two questions, if I can quickly do that. One of them you will like because it's about the past, but the other one you will not like because it's about the future. Do you plan to do this in a reanalysis context, so that you rerun a lot of so for the far past, the whole thing?
Yes, yes, yeah. We are doing it for with a reanalysis or a hindcast. The only problem there is, of course, that the early observation in Norway, for instance, they start in 2010. The citizen observation is even, they start more or less in 2018. And when you use reanalysis and your objective is climate, you need to keep a very close control of the time consistency. So it's, for that I have different solutions to make the data set a bit more time consistent. So it's not only this, but you really need to be sure that your climatological trends are kept.
Okay, I see. And the other one, I was really surprised to see that your analysis can be used to improve the forecast as well. Because usually if you pull your analysis too close to the observations, then you might get some imbalances in the initial state, and the model then at the very first hours improves, but then it gets worse. And I wanted to ask this, then why is it not used in the NWP if it's so much better to use your analysis than the...
Yeah, maybe I was not completely clear, but when I say that you're right, there is a benefit in using the analysis, but the people here, they're not actually rerunning the model using the analysis, but there's post-processing the output of the model run based on the analysis. So it's a statistical post-processing with some simple methods, and even with basically you are adjusting the forecast given the difference between the background and this analysis. So you are transporting a bit this difference in time.
I see.
But there is also people that is they are using this analysis as a forcing for the soil model for the next model run, and they show that there is some benefit. There is a paper out from some of my colleagues, and they use this as a boundary condition for the next model run, and you gain some skill.
Thank you.
Other questions or comments? Yes.
Thanks for the insight in your work. I'm wondering, you had this schematic figure where you showed the uncertainty of the observation and of the ensemble. I'm wondering a little bit how you assign the uncertainty to the observation. Is it then spatially different, or is it time
Which
dependent?
one?
There was one schematic where you had this huge ensemble on top and observation with the blue circle. Yes, this one.
Yeah, how can we assess the observation uncertainty? It's a prior in the scheme. So in a sense, it comes from our own assessment. And you're right, that's all we have to do in this scheme is not really assign an uncertainty to the observation, but say to the scheme how much we trust more the observation compared to the background. So if you trust twice as much, if you trust it 10 times as much, this kind of regulate the way you approach the observation. You can go closer to the observation if you reduce the uncertainty of the observation. You can stay closer to the background if you increase the uncertainty. So it's a prior assumption that you can verify with the posterior of distribution. So you need to play a bit with these two fields, let's say with these two parameters, such that your prior assumption is matched by the posterior. But anyway, you can also do some diagnostic. Since you have so many observations, you can have an idea of the representativity error by taking the standard deviation. For precipitation, you can have the precipitation intensity. Let's say you use the WMO station, the observation network that you trust. Then you have a lot of net atmos surrounding the WMO station, and you can have, for the different value of the WMO station, you can have a standard deviation given by the variability of the citizen data. And this give you you will see that when it's raining small, the variability is small. When it's raining a lot, the variability is higher. And you can really see the multiplicative nature of the uncertainty for precipitation because you have so many stations. So there are a few techniques that you can employ.
Thanks. And if I may, a short follow-up question. You had this scatter plot where you plotted the observation against the analysis, and there were some clear horizontal line in the analysis. Is this because the analysis is only having thresholds, or
here?
Yes, here.
This is, you mean this clear horizontal line here?
Yes.
That's the analysis is smoothing in this case. So then any spatial analysis method, it tends to smooth a bit the extremes, right? So here the observation goes to 40 millimeter. You can believe it or not, because maybe it's one single observation can be very local. But most of the observation, the analysis stop at 20. So it means that we are not able, and this is an effect of the smoothing of the...
I understand that, but there are clear gaps in between the plots, so it seems to be some kind of categories or...
Yeah, you're right. It might also be because I'm taking a rounding of
okay. Yeah, that's what Maxime also was suggesting. Thanks.
Digit or so. Yes, could be that. I will look into it.
And for curiosity, if you just use the citizen data and not the WMO data, what is the result?
First result will be that my colleagues working on the station network will be not really happy.
Okay.
Okay. But the second result will be that, yeah, we do this exercise to assess the quality, because the WMO station are actually the one we trust. So our diagnostic that we do every day is we take away the WMO station, we use only the NetAtmo, and we assess the uncertainty. But the NetAtmo station are the number is so big that the WMO station, I must say, locally is very different. Very hard to make them make a difference, because in some places you have Bergen, Oslo, you have 3 high quality stations and 1,000. So you will assign, if you really want the WMO station to have a much higher weight, you must trust that value, I don't know, thousands of times the opportunistic measurement. And yeah, they have a very important weight in the quality control. So we try to throw away data that are not in agreement with them. But the data that are left, they should give us a kind of a way to infer the spatial pattern given the WMO station, which is at the center. So in the method itself, they don't make a difference, but in the quality control, you can use it.
Okay. Okay, thank you very much. Well, quickly, very quickly.
Thank you. I was just wondering, with the inversion, like when there is a cold air in a valley, and you change the model, and then you like display a graph for a certain place in the valley, and you follow the observation, so you push it down, but then it, like in 3, 4, 5, 6, 10 hours, it goes back to the model. So then there will be like increase in the temperature, like during the day or in the next hours, but it might not be the case. So the graph might not be correct. Like
yeah, that's the whole point about statistical post-processing is that risk, right? You change something which can become then unphysical. So it's a matter of tuning in a good way the statistical post-processing. But for that, but there is that risk, definitely.
Thank you.
Okay, thank you very much again, Christian, and we can now move to the coffee break. c'est sans doute une discipline que vous avez. Comment bien? Deuxième, hey!
So as it's your,
Mine.
it's your,
Mine. Do you have yours?
I should go with mine.
Yeah. Yeah. Do you have all the presentations on your computer, or just ask the presenters if they want to use their own?
I have 3 of them. But I need my own.
I was also going to ask this question. When you are sharing, you have to use your own laptops. There are no laptops provided.
Well, the one with Sophie.
No, she's here. She wasn't here this morning. So I'm sharing the first session tomorrow, so that's why I have to be there. Do you have to do anything to get things working? Some magic?
Hi. So we have to use our own laptops here. So I didn't know that.
Are you the chair, or
Yes, I'm the chair.
so
But
can
I
we
thought-
upload to your laptop, or should we?
Yeah. We can upload here. The others from my session have sent me via email.
I have a USB.
Yeah, no problem. Yeah.
We generate a very similar Liesner analysis. And this is really interesting. We could process it in Nowcasting.
This is probably. Yeah, we can do yours before. Here, the first one.
It's a problem. I can.
This one, I guess. Okay.
But I got feedback from some of the
Old HU stick.
10 Jahre, 10 Jahre.
Ja.
2014. Naja, der Plastik löst sich langsam aus.
Ja, aber-
Diese Weichmacher.
Mhm.
Chair.
So maybe
The next one.
maybe you could you know that it's some people that are following us on video stream. And they said
Yes.
that the sound was a little bit low. So
The sound. Okay.
the sound from
Because
here.
of this one.
So yeah. So it's like this. Could you just test it? Alexander, and we will stand back there and see if you hear it. We hear you.
Yeah, you can.
In your eyes.
Is it? Oh, is
No,
it
no.
on your eyes?
Yeah.
And it should be. Is it okay?
Okay.
Yeah, for me it's
Yeah.
a bit like at the doctor with the. Yeah. And I should speak. Yeah. So I'm just downloading. Yes, I can talk. Do you hear me? Yes. So the presenters should use this one.
And then can move.
And then.
Better.
Mm-hmm.
That's nice. It's the presenter. Is that one? And you can use
The microphone.
yeah.
Yeah.
Mm. So it's in your
Also.
yeah. So as you see, it's this should be behind the ears.
Yes.
Yeah.
Mhm.
And so only this you see that it's mute there. So just
Okay, it's
so now
unmute.
it's mute.
So good. Hi, hallo. Habe ich schon gerade jetzt runtergeladen, Ihre Desktop. Sollte alles klappen.
to zadzwoń. Słyszysz? No zadzwoń. Co jest grane? No halo, słucham się. Słyszysz mnie?
1, 2. Can you hear me? Yes. Good. Held. Good.
So, good morning also from my side. Let's continue now with our nowcasting and post-processing session. It's keynote time, so we start with the first keynote talk in this part of the session from Jonas Bend about advancing weather forecasting with statistical post-processing. Please, thanks.
Thank you. Welcome everybody to the second part of the morning session. So I'm going to present us a few opportunities and limitations, a few lessons learned, if you will, from our introduction of statistical post-processing at Meteo Swiss. Before we go into the challenges and maybe things that worked well, I'd like to provide a short overview of what we did. So as you can see in this sketch, we tried to combine with post-processing the information from our different numerical weather prediction models into one consolidated probabilistic forecast data stream available everywhere in Switzerland, so for observed and unobserved locations, which we then use to feed into our data distribution system and to show up in our mobile app and on our website. That was basically the goal. And how we did this, we use tried and tested methods at the time when we started the project, which was basically EMOS. We used this in a global setting, so one joint model for all locations to be able to produce predictions everywhere. In a multi-model setting, also we combine information from all available models at a given time. So these are currently ICON at 1 and 2 kilometers that we run out to 1.5 and 5 days respectively. And then beyond that, we have IFS. To account for local effects, we also add information from digital elevation models through topographic predictors, such as topographic position index that tells you a bit about whether you're on a mountaintop or in a valley, which is quite relevant in Switzerland, right, as you might expect. We do station-based training against roughly a few hundred stations in Switzerland and nearby surroundings, and we do this for wind, clouds, and precipitation. We also developed a method for temperature, but because we had already a post-processing available in our automatic forecasting at the time, we didn't replace that, and because we couldn't beat it at the stations, basically. This was using local post-processing. Now let's have a quick look at what this looks like. So on the left, you can see for a specific case, wind speed forecast, October last year, when we still had Cosmo models available. You can see the NWP data for a specific location in Switzerland. And you can see that the higher resolution model gets sort of the intensity of the wind speed on this ridge a bit better. The lower resolution models struggle quite a bit. Also, you could argue that these are not calibrated well. The spread is apparently quite small. So what the post-processing then does is provide one consensus forecast that is free from bias, mostly seamless, although I have to add, we don't do anything specific to guarantee it's seamless. So there is instances where you can see jumps from one model to the next, and it's calibrated. So far, so good. Now, by way of outline, a few of the opportunities and challenges I would like to talk about today. First and foremost, post-processing provides us with improved forecasts. So the data-driven forecasting allows for targeted optimization, and we get better scores. But there's also a few challenges. First and foremost, we have a change in forecast characteristics. We may have inconsistencies across applications with and without post-processing. And then there's the whole large field of operational challenges of the complexity that you introduce when you go towards data-driven forecasting. Just one quick slide to show how post-processed forecasts score higher. This is our headline score that we report to the federal government 4 times a year to prove that we're doing a good job, right? And you can see the evolution of that headline score for 1 day, 3 day, and 5 days out over the past 10 years. And sort of in the colors is shown how much we are above the target. So we have to fulfill a few targets for these, or targets for this headline score. And you can see there's 2 vertical lines. One is when we introduced fully automated forecasting in 2021. This was a bit rushed. So there were a few issues in the beginning that got fixed rather quickly in the first weeks or months of introducing automated forecasting without post-processing, I should mention, right? Because we averaged this headline score over 12 months, you can see the effect quite for a while. And then the second vertical line is when we introduced post-processing. We were already producing forecasts with considerable quality with respect to the headline score, so the post-processing didn't add a lot. But what you can also see that ever since we went to automated forecasting and fixed the first issues that we had and introduced post-processing, we're way above the target. So we could even afford to lower the quality a bit and wouldn't be in trouble, right? Now to the first issue, the change in forecast characteristics. So basically what happened is the legacy system was using mostly direct model output at, well, the resolution available. You can see this on the left for wind speed. This is Cosmo 2, so the 2-kilometer grid. And then we introduced post-processing at stations, and we went to kind of like hyper-local forecast by adding all this additional information on topography, etc. You can see a visualization of what that would look like if we were to produce this on the grid, which we don't. You can also see where, at which points in Switzerland, this is just a small cutout of the Alps in southern Switzerland. This information is available in the app and on the website. And obviously what happened when you go from a product that has a spatial support of grid or area to a product that has a spatial support more of point, is you increase the spread, you have a lot of more variability, both sort of in the uncertainty quantification for the forecast, but also from point to point if you move around in space, right? And this was causing a bit of problems, and we got quite a bit of negative feedback from users because of that, because mostly the forecasts that they were used to changed once you introduce post-processing, right? We try to alleviate for that or mitigate that by introducing more and more probabilistic visualizations in the app. Just a recent update has seen a few more additions. You can see it here. We added ranges for precipitation in the daily overview. We added precipitation probability in the sort of time series view to emphasize more the uncertainty component of the forecast. Unfortunately, this is a bit an ongoing effort. It's also a bit an uphill battle because there's strong pressure to keep all the visualizations the same, to not overload it, to be cautious about what we can communicate to the general public, which is probably a good thing too, as I just mentioned before. I mean, change always is a bit disruptive, right? Another aspect where we struggled with the change in characteristics is the pictograms. So if we go back quickly, you see these are sort of an important part of, I guess, the weather app, right? People look at these symbols to have a feeling for what the weather brings. Due to the changes in forecast characteristics, the decision tree producing these pictograms had to be retuned. And unfortunately, we don't have a sophisticated verification for pictograms available as of yet. We're working on this, but it's not ready yet and hasn't been ready at the time when we introduced the post-processing. But what we could do is just look at sort of the climatological frequency of different pictograms and try to keep this roughly the same, such that we don't sort of lose the individual pictograms, that they still show up with the relative frequency we would expect. Here's another aspect that needed changing. So before we introduced post-processing For example, the rain in the pictogram was based on 3 hourly probabilities of rain and then aggregated to daily. So you always had consistency from the 3 hourly to the daily. This worked because NWP, as you all know, are underdispersive, so they're basically behaving much more like a deterministic forecast than maybe a fully probabilistic forecast at the point. When we moved to post-processing, this changed quite dramatically. And now we had to change this approach. So basically the pictogram of the daily pictogram and the 3 hourly pictogram are now based on the respective probabilities. So you can have differences in the 3 hourly and the daily, as you can see here. So in the time series overview, you don't see any rain because the probability for any 3 hour period is fairly low. In the daily overview, you have rain because it's reasonably certain that it's going to rain during the day. Not all things in terms of changing characteristics were bad or difficult, though. I mean, one thing that was quite nice to see is post-processed forecasts are less jumpy. And in particular in convective situations, this is an example of a convective situation in the south of Switzerland, rainfall in late summer. And if you focus on the left, well, on the end of the time period that is now getting hidden slowly, you can see that the forecast from the legacy system, which is just direct model output, jumps around quite a bit with every new NWP simulation becoming available, whereas the post-processed forecast stays much more consistent throughout time, and this is also by users perceived as an improvement, right? Now to the next challenge, the inconsistencies between different products. So one thing we were aware of even before we introduced it, but that got a bit more pressing when we had a few different strong wind events earlier this year in winter. So we had a series of firn storms in late winter or early spring this year. And there we noticed that, well, there was this situation where you have like firn, this is very localized, it's in a few valleys only in the Alps where you get the strongest winds, right? And there was a warning out of level 3 or even level 4 at one instance of this firn storm, and high resolution NWP, so Cosmo 1 at the time, was doing a pretty good job at this one station that I picked to illustrate the problem, right? As you can see here on the left, our post-processing wasn't doing quite so well, and this was causing quite a bit of discussion how we can improve this, because it's unfortunate, because we also know that a lot of people look strongly to these local forecasts, and even if the warning is out, they may still go and check the wind speed and then make uninformed decisions, or decisions not based on the best information, right? We understand why this was happening, right? So the high resolution NWP system tends to overestimate the wind gusts, so the post-processing has already sort of the tendency to reduce the wind peaks. It does this even more so in situations with strong winds, because these are generally rare and less predictable. And it mixes in lower resolution information, which in these cases of firn just don't see the high peaks. So this all led to this sort of strong reduction in wind gust in the post-processing. Luckily, we already had a collaboration set up before, trying to tackle this, because we have seen this coming, right? So this is a collaboration we did together with Sam Allen, Johanna Ziegel, and David Gainsbourg from University of Bern then. And we were looking into how we can improve post-processing for high-impact weather. And we did a few experiments with simple post-processing, and so here's a few of the findings, right? So we can improve forecasts for high-impact events by using weighted scoring rules, and this was already known, right? Or you could also do scale the loss function according to how impactful a forecast observation pair is, which is kind of similar to using weighted scoring rules. And we can even combine different models, so such models for focusing on high impact weather and models more for like general weather, without degrading the overall forecast performance, so that we can come up with a combination of these. And we found a nice way to visualize these trade-offs, and this is these multi-objective plots. Here is an example just for For a simple analysis that we did on wind speeds and rainfall, it works for both parameters reasonably well and looks fairly similar. So here what you can see is on the x-axis the scores for general weather, or the average CRPS if you so want, the average forecast accuracy. To the left is better, right? On the y-axis you see the performance for high impact weather using a threshold weighted CRPS in this case. And where you want to get is to the lower left corner, and you can see that the direct model output is in the upper right corner, so post-processing improves in any way. So maybe the interesting bit is now here, the blue point is if we just optimize, if you use as a loss function in the post-processing the CRPS, which is just optimizing for average performance, right? So we get a pretty good average performance, but not optimal performance in case of high impact weather. If we use a threshold weighted loss function, focus more on high impact weather, then we get better performance for high impact weather and slightly worse performance on average. And we can use different approaches to mix these two or combine these two solutions into one post-processing and go further to that lower left corner. Unfortunately, those results are not published. We didn't manage to also do this with more complex post-processing approaches, for which we hope that this could be done in one go. So if anybody has time or is interested to look more into this, there's clearly still some work to do. So this allowed us to quickly introduce this focus on high impact events in our operational post-processing. Here's a plot that's maybe a bit hard to read, but what we basically did is we looked at the forecast performance for wind gusts in our post-processing, stratified by observed wind speeds. So this is not something you want to do in training, but maybe for diagnostics it's okay. So you have a kind of the same set of samples for the different models that you look at in the stratification. And what you can see is if we do a mild threshold weighting in the loss function for the training for the post-processing of wind gusts, so this is far away from being warning relevant, right? This is just to exclude the sort of lowest wind speeds that are hard to predict, that are not really interesting. I mean, nobody looks at gusts when it's not windy, right? And we also did, we used, instead of hourly maximum wind gusts as a target quantity, we used 3 hourly maxima to increase a bit the predictability of the feature. And you can see by comparing the blue and pink lines, I should move on, right? The blue is the original post-processing that we had in operation also during these Föhn events, and the pink one is the threshold-weighted one. And what you see is that, yes, indeed, you can remove a bit of the negative bias in high wind speed situations, and you can improve the quality in those situations. It's a step in the right direction, but it's obviously nowhere near from being perfect or enough, so we will keep looking into this. Another area where inconsistencies hit, obviously, is when you have different products, one with post-processing, the other without. So we have these local forecasts. I've only been talking about these local or point forecasts so far. These is where we use the post-processing. This is also the most used product on our mobile app. We have like 1 billion hits a year. So this is really used a lot. On the other hand, we also have a radar animation that is extrapolated, that is quite often used. So this is the second most used product on the app. And this is just using, well, nowcasting and then blending into the control run of the high resolution simulation. So obviously you have all these situations where you have in the pictograms, in the rainfall probability, some information about rain not being very likely, and in the radar animation you see, well, there's a cell, right? And imminent or predicted to appear in the next few hours. So this is also one area where we want to improve in the future, and Lionel will talk more about this tomorrow, about our plans for sort of combining nowcasting, post-processing, and moving a step forward in this area. So for the last few minutes, I would like to also talk about a bit about the operational challenges, and most notably, we changed in the last months from using Cosmo as our high-resolution NWP to Icon. So this had quite dramatic changes in terms of the model inputs related to less smoothing of the topography and icon because of the triangular grid. So in essence, even though the nominal resolution of the models is the same, sort of the actual resolution that you see in the data or the detail you see in the data has improved quite a bit with icon. And also some of the parameterizations have been changed. So it was clear from the beginning that we need to retrain the post-processing to also profit from these changes. We pushed hard to get some reforecasts. In the end, we managed to get 3.5 years of reforecasts with icon 1 and 2 ensembles on a thinned out schedule, which was a huge effort compute-wise, also data management. We had parallel phase where we had pre-operational icon, operational Cosmo, and reforecasts coming in at the same time through data distribution and into the database, which was really a challenge. And all this under time pressure, right? So it had to happen quickly because everybody wanted to move on with moving this into production. We were very happy to see that in the end our scorecards were mostly green. So even though we probably couldn't fully profit from the improved quality of icon, we at least didn't degrade in the post-process forecast because we had much longer training samples for Cosmo available. We had much more time to develop those methods compared to icon. So we were quite happy. And recently introduced this just to hear in the last weeks that, well, we have an issue with ensemble perturbations in icon. We have too much spread. That's for the first time in my professional career that I see that a model change is motivated by too much spread in precipitation, unrealistically high precipitation intensities in some instances, and we have to fix this, which obviously renders all these reforecasts a little bit more useless, right? So, yeah. So there's the big question for us currently is how do we deal with future NWP changes? It's very clear that we can't afford to do this reforecasting exercise for every model change, so we will probably never do that again, right? Our current best bet is to use fine-tuning to sort of evolve data-driven forecasting on the fly. This then requires better monitoring so that you can safeguard against runaway effects, against drifts, etc. We also have to somehow integrate version information in the predictors so that we can go back and retrain with old and new data, well, different model versions. This is still an open topic, how we best do this, in particular because we also often know that a specific NWP upgrade affects mostly one parameter and not the other, right? So it would be nice to also be able to use that kind of information, or at least learn it, right? And first and foremost, what it already led to is that sort of we have moved much closer together with the modeling division at Meteo Swiss, and we're co-developing more the NW or coordinating the NWP changes and the post-processing. We have additional requirements on parallel phase, on test periods, etc., so that we can make sure that we also can guarantee the quality of the post-processed forecasts with changing NWP. With this, I'm at the end. As a summary, well, data-driven forecasting leads to improved scores. The benefit for the users is much less clear. So there's inconsistencies, there may be changing characteristics, it's much more rapidly evolving, which for especially experienced users is difficult because they often learn how to use our forecasts, and then if you change them, that's not necessarily something they're looking for. We try to mitigate a bit by providing more information about the nature of the forecast, about probability, about uncertainty. And we probably in the future also need to do some form of multi-objective optimization to address different aspects that are important in terms of forecast quality. On the other hand, there's new requirements coming in from data-driven forecasting, which relate to, well, one was this co-development with the numerical weather prediction divisions, right? And the increasing importance of data management and monitoring as such when you do data-driven forecasting, just because that's what you rely on, right? With that, I'd like to conclude. Thank you for your attention.
Many thanks. Very interesting talk, and also the insights in the daily life of our work is very interesting. Yes. Are there any questions, comments? Yeah.
Thanks for the good presentation and for giving a broad overview of all the things you're doing. And I'm a bit ashamed of my question because it's another thing to add in on your to-do list. But I want to ask, not only for you, but to the audience. After extreme events, it comes more often now that the people are asking how much was due to climate change and how much was due to the weather. So climate attribution is becoming more and more important, and the people will find natural to use the model of today to assess these type of things. But I don't think we are here at the moment because time consistency is not an issue. But I was simply wondering if climate attribution is something that you have in view on your work, or if it's on your to-do list, or if you have, you have so many things to do that maybe it's a low priority task.
Yeah, thanks a lot for the question. Yes, it is on our list. It's not in our team, so I'm part of the post-processing and verification team, so the climate attribution work is mostly happening in the climate division at Meteo Swiss, and I know that there's updates also for the app planned to bring together sort of the forecasts and the climate information more, so that it is easier to put the current weather into context of the climate. This is a first step. It's not a sort of full-fledged attribution that allows you to quantify how much of the recent event could have been to climate change and the risk of that, etc. But yeah, we're working in that direction.
Any other questions? Yeah.
I'm just wondering how do you communicate about the inconsistency to the users?
Yes, that's a good question. Well, I mean, we communicated through our blog, which is read quite a lot, on the introduction of post-processing, and we already there pointed out that you shouldn't use post-processed information in case of warnings currently. But other than that, we're not very offensive in communicating, do not use this product, right? This is something we identified as kind of a weakness of our current system, not necessarily directly related to post-processing. Earlier this year, we also had incidents with data quality where just some parts of the pipeline didn't work, and then for an extensive period of time, a few hours in the day, the forecasts were not updated or not available, and we knew that, and we had no way of showing in the app that, well, this is actually not the right information, you shouldn't look at this, right? We have a technical problem. And then, well, after a few hours, this was being made available, so maybe there's some scope to also use similar procedures in situations where we know that the post-processing is deficient.
I was also thinking about like the difference between the daily symbol and the 3-hour symbols, or things that are more...
Yeah, ever since we introduced that, we didn't get a lot of comments on that, so people seem to be okay.
Thanks.
Yeah.
Thanks. I just wanted to kind of expand on that question around consistencies of a product. So you have inconsistencies between the post-processed and non-post-processed parameters. Do you also have inconsistencies in the post-processed parameters, for example, temperature and precip type?
Yeah, for sure.
And how do your users, or what do your users think of that? Is it important to them?
Yeah, it's a difficult question. I mean, most of the feedback we get is negative anyway, right? I mean, we rarely ever get positive feedback. If people are happy, they're just happy and don't provide feedback. If they're unhappy, they usually voice their concerns. What we know is that sort of more technical users, like downstream applications, impact modelers, etc., they obviously care a lot about consistency, but from the general public, I don't really have a good answer whether this is important or not. There's cases where people complain, yes, and there's also cases where we are sometimes a bit subject of ridicule and jokes, right? When again something happens that it's not the first time that you forecast rain and there's no rain, or the other way around. Yeah, that's kind of things those happen. But yeah, I don't think it's a huge problem at the moment.
Okay, thanks. It's similar in the UK. Most of our feedback on our public-facing things is around chemtrails and geoengineering and other such nonsense, not related to the forecast.
Yeah, yeah, sort of in that sense, right? When we change visualizations, when we add things in the app or remove things in the app, that generates much more feedback than if the quality of the forecast changes, right? So the introduction of post-processing, there was not a lot of feedback, but then as soon as you introduce a new element in the app or rearrange some of the tiles or something, then there's lots of complaints.
Any more? Yeah, Markus, for sure.
Thanks, Jens. You showed, of course, the most unpleasant example for post-processor, the Föhn event, and I hoped that you have a backup slide with your improved forecast for that. And if not, maybe later. But the question is now, maybe I missed it, but do you turn off your threshold-based scoring now and accept that probably your headline score will get worse a little bit? Because you showed the CRBS gets a little worse, but the headline could get way worse in general, right?
No, yeah, we're in a kind of comfortable situation there in that the headline score is not based on wind gusts, it's based on wind speed, and it's also based on the maximum wind speed during the maximum hourly wind speed during the day. So it's already kind of, if we improve sort of the strong wind situation, we usually also improve the headline score. Overall, that change had barely an effect on the headline score. We did do some very weak threshold weighting also for wind speed, not just for gusts. But yeah, that was not having a great effect. But surely, if we push this further, and if we try to get really better forecasts for Föhn events, in particular, I think we also have to change the approach and add more information to be able to do so. And unfortunately, no, it's a good point. We should also provide that backup slide with the improved forecasts. It's still not going to be great, though. I mean.
Thank you for a very nice presentation. I was just wondering, when you said you're getting feedback from users, do you have a platform how you meet with your users and how you collect those feedback, and how do you integrate the user feedback to improve your visualization or anything you mentioned? Thank you.
Yeah, thanks a lot for that question. We do have obviously some ways of interacting with the users, but I would say, as a very quick answer, this is not an area where we're very strong at the moment. So I think we should improve on that and try and get more feedback on whether our forecasts are useful and what users really need to better make use of our forecasts, because that's something we often try to second guess, but we don't have really good evidence, right? So yeah.
Okay, I think we should continue. And next, speaker Sebastian Lerch about graph neural networks for post-processing.
Great, thanks. Like this? Yeah. Okay, thanks. Thank you for organizing this conference. It's a great follow-up to one post-processing meeting we had in Belgium 5 years ago. I'm going to present our recent work on graph neural networks for post-processing. This is joint work with 2 colleagues at KIT. It's mainly the work of Moritz Feig, who was a bachelor student who did this as his bachelor thesis project, and he was an exceptionally good student, so we tried hard to hire him later on as a student research assistant and turned this into a paper. And this is also joint work with Jan Stümer, who is a colleague and an expert on geometric deep learning. Now, before I start, I want to interject a small advertisement slide here, because we do have a postdoc position at KIT available for 3 years, working on AI-based post-processing and impact-based models for hydrological applications. So if any of this, which I'm going to talk about, seems interesting, then please talk to me, or if you know anyone, then please let me know. But back to what we are doing. So the starting point of this was that we were thinking about how location information is being used in post-processing models. And one point where this comes in is in the estimation of models, because models could be estimated globally, which means that you pool data from all available locations or all available stations to fit one single model, like Jonas just showed. Maybe you have like location-specific predictors that make your model somewhat locally adaptive. Or the other extreme point would be a local model, which means you estimate a separate model at every single location, which is then very location-specific and will often result in better performance compared to a simple global model. Now, there are variants sort of in between forms of this. One is like what Marcos has been doing, the Samos approach, where you compute locally anomalies and then use those in post-processing. There are also ideas that you could group together stations that are similar in some sense, or do some clustering and then post-process from these groups and clusters of stations. And there are very other ideas of doing something in between local and global models, including newer neural network-based models, such as these distributional regression networks that you heard about, that we have been developing, or something like BQN that John has been developing in BetNet Norway, where you typically train one global model, but you make the model in some sense locally adaptive by using some methods from the machine learning literature, such as these embeddings here. So that's how our DRN model looks like. I'm showing this here because this will later be used as a benchmark for our graph neural network models. So in principle, that's a neural network-based post-processing model. It's a fairly simple neural network architecture, so fully connected feed-forward neural network. Output here are distribution parameters. So this is for temperature forecasting. So we assume that the target is a Gaussian distribution. We just predict the location and scale parameter of that distribution. As an input, we use station-specific predictions from the NWP model. We have information about the station, things like coordinates and altitude of the station. And we fit one single model jointly at all locations, but we use these embeddings here to make the model locally adaptive. We take this idea from large language models, where we map every single station ID, which is a deterministic information, to a vector of latent features or real values, which are then used as additional input to the model and aim at making this model locally adaptive. As I said, this will later be used as a benchmark model. All the details are borrowed from another paper that we wrote also from the beginning of this year by Kevin Höhlein, which I'll also come back to later on. So the motivation for what we are doing here is that despite maybe using location information as an input to a model or training a model jointly for multiple locations, still most post-processing methods operate only on a single location at a time, which means that they are typically unable to, on the one hand, extract information about spatial structures in the forecast errors and use that information. And on the other hand, they're also unable to share somehow information across stations, because information can't flow from one station to the other if you're doing post-processing sort of station by station wise. There are spatial methods that at least partly address the first aspect to some extent. They are usually aiming at multivariate post-processing. These can be methods from spatial statistics, where you model, for example, model parameters as spatial fields, things like Annette has been working on, or Kira Feldman and others have been doing. And there now have been lots of CNN-based approaches to post-processing, so based on convolutional neural networks, where you typically do this in sort of a grid-by-grid fashion, which allow to use spatial inputs, but still do not allow to sort of share information across location or have information flow from one location to the other. And they are not really, it's not really clear how to use them on a regular grid. And that's where sort of our idea came in. This was our starting point, because many of you have likely seen graph neural networks emerging as a new kind of neural network architecture, and we wanted to try to use this for post-processing. So where the idea is that we represent stations on the nodes as the nodes of a graph, and then information should be able to be exchanged across this graph between stations. To explain what we do, I will start with a short explanation of what a graph neural network and what a graph in the first place is, and then talk about how those have been used in different applications, and then how we actually use them and adapt this for post-processing. So, graph neural networks are, as the name suggests, neural networks for data that can be represented as a graph. And typically the aim is in the end to make a prediction with those models. This can be a graph level prediction, meaning that you make one prediction for the whole graph, or a node level prediction where you make a prediction at every single node. And we will do the latter. So here is like what a graph looks like. These points or circles are the nodes on a graph. Later, in our case, this will be the stations. And these stations or the nodes are equipped with some sort of attributes. This can be information about the station, like the coordinates, the altitude of the station. And this can also be like the station-based predictions from the NWP model. And then these different nodes or stations, they are linked. These links can also carry information. They can have directions, they can be undirected. And for example, we use something like the distance or the inverse distance between two stations as an information that is on the link or the edge in the graph. And then all of these together form the whole graph, and you can still have some sort of global attributes of the graph. Something like the day of the year could be a global information that's shared across all of the different stations. And a key design element of graph neural networks now is the so-called message passing, which means that the graph neural networks enable information to flow from one node to another node. So the nodes iteratively update their learned representations by exchanging informations across this graph of stations, which now is something that is not really possible in standard post-processing models. And a lot of these architectures have been proposed. They differ, for example, in the way this message passing then actually works. I will come back to this in a second, but first I would like to show some examples of data that can be represented as graphs and where these type of models have been used in the literature. So one popular example, sort of more classical from graph theory, are social networks. Here is one example from a play, Othello, where you can represent interactions between characters via a graph. So this can be just a simple adjacency matrix, who interacts with who, or this can be also somehow you can introduce a distance or a direction or a kind of interaction if you want. So these are not really suitable for machine learning purposes though, because for every social network you just get a single graph and you can't really do much learning with a single graph. Another example where this has been very prominently used in science applications is for modeling molecules. So a molecule is represented again as a graph because you have different types of molecules that share connections between each other. You can have like distances between these connections as attributes to these edges in the graph, and then you can make a prediction, for example, for the whole graph of how a certain reaction with another molecule would look like, or where this reaction is going to take place as a node level prediction. And that's something where these type of models have been used extensively. And they have also made their way into weather forecasting. Many of you will have seen the GraphCast model. You've seen the poster by Matthew Smith outside on doing something similar for Nowcasting, where you use graphs for weather forecasting and you represent grid points as nodes on a graph and share some information between those. Now, as I told you, there are different types of these graph neural networks. They mainly differ by the way in which this exchange of information works. I've used here an image with 3 different common flavors of these GNN models. It's probably a bit hard to understand this when you see this for the first time, but you can take a look at this paper, which has a very nice broad introduction to this. I just want to try to convey this basic idea. So what you see is you can see a small part of a graph, and you have some central node that's marked in red, and these neighbors that are marked in blue. And what happens now in this message passing step is that in the central node, you aggregate information from the neighborhood. So this huge circle with a plus inside is some sort of aggregation function that collects information, and that's supposed to be a permutation variant. Could be something like a sum or a mean operator, for example. And what you now do is to get the updated representation at some node u, you collect the information from all the neighbors to u. So this nu is some neighborhood of this central node u. And what you do in this convolutional flavor, you just multiply the representation with a constant. So the CUV is just a constant that depends on u and v, and you can apply some functions around this. So these psi and phi are learnable functions, so also some sort of neural networks inside the whole graph neural network. But you can make this more complex if you want. So you can use an attentional flavor where you don't just have a constant, but you learn a function that depends on the representations at u and v. Or you can make this even more complex if you want, so you can do also the message passing flavor, where you just have this as a very general function that's no longer just a multiplicative learned function. So we tried different versions of those. What I will be showing will be using this attentional flavor later on, but especially in the bachelor thesis by Moritz, we looked at different versions of this. Differences are not large, but exist. So I'll be focusing on the EUPP bench dataset that Jonathan presented earlier today. So just as a quick reminder, we have forecasts and reforecasts, which differ in the number of members. We do all of this for 2 meter temperature only. We have 31 predictor variables as inputs. We here focus on 3 different lead times and those stations. I'm sorry for the Swiss colleagues that we left out Switzerland, but the station data was a little bit more difficult to use there. And what we do is we define 2 tasks. So on the one hand, we use the task from the benchmark idea, which was the reforecast to forecast task, which means that you train a model based on reforecast and apply this to the forecasts. And we also use the reforecast to reforecast task, where we train the model on the first portion of reforecast and apply it to the last portion of reforecasts. Now, one side aspect that I wanted to mention here, because Jonathan brought this up also yesterday in the discussion, is that while doing this, we realized mainly our own issues in using the data, because we tried to reproduce the results from one of our earlier papers, and we failed to do this because of the data preprocessing that we used. So we realized that it seems like this EUPP bench dataset is being used now in different papers, but everybody does their own preprocessing and does things a tiny bit differently, which means that the results are not necessarily identical and easy to reproduce. So what we are working on is to do what we did here and produce like a pre-processed version of station-based forecasts and corresponding observations together with these predefined tasks as a simple-to-use data frame specifically for machine learning purposes. If you're interested in using this or in rerunning your models that you did run for the original benchmark and applying to this, just get in touch. I will also get in touch with you if you participated in the benchmark and did run some models, and maybe ask you to rerun your models if you're interested. But this is just as a side note. So now the interesting question, of course, is how do we now adapt these graph neural network models to our data set and what we are doing? And I'm trying to explain this step by step, even though the whole architecture in the end will be a bit more involved. So our first step is, of course, to generate these graphs that we now then want the neural network model to operate on. So what we do is we represent, of course, our stations, as I told you, as nodes in the graph. We represent the station ID and the features by the sort of learned representation. We use some sort of embedding in the sense. And of course, we have to decide how we connect the different nodes in the stations. There are many different ways to do this. We just chose a very simple distance-based criterion. We just pick a threshold, and 2 stations are connected if they are closer than the sort of maximum thresholds. There are different ways to do this. We just tried out a few threshold values, looked at the results when we do the model training and validation. But this is not systematically tuned, and I'll come back to this point later on. We do this in a member-by-member fashion. So we build one graph for every member, and then we connect these graphs also across the different members. So what you will see here is sort of a small schematic sketch of a subgraph where you have the different locations, that's the first argument, and you have the different members, that's the second argument of all these nodes. And we have these NWP forecasts plus the learned embeddings at every single graph. So this means that we now have a graph, but we still have no graph neural network model. So this is where now these GNN blocks come in. As I told you, we're using graph attention layers, which perform this message passing in this attention-based message passing flavor. We do capital K of these blocks to allow information to flow multiple steps. So if you have one of these GNN blocks, this means that you can have just information flowing from one neighboring station to another neighboring stations, but we of course want the model to be able to transport information across multiple steps. So we use multiple of these blocks, and we use some sort of RESTnet-like skip connections inside these blocks, which just turned out to improve the performance a little bit. So this means, in the end, after performing these K graph neural network blocks, we end up with our graph, and we have these learned representations. But if we think about the end product that we ideally want to have, is that we want to make a node level prediction. So at every single node, we want to make a probabilistic forecast. Here we choose this to be distribution based, so meaning that we still again assume a Gaussian distribution because we are modeling temperature. We want to predict the location and escape parameter at every single distribution, which means that we have to get somehow from our learned representation to our distribution parameters. And for this we use an aggregation procedure called deep sets. So again, another like neural network type model inside the graph neural network model, which takes for one station all these learned representations from all members and applies a relatively simple neural network based aggregation method. So this deep set ensures that it's sort of permutation invariant because we do not want to have as an important feature which member had which exact prediction. We want to treat them as interchangeable. So we apply this, we get out our station-based forecast distribution parameters. Now, one side note of this is if we do this for the reforecast to reforecast task, that's simple because we have the same number of members in the input, in the training data, and in the test data. If we do this for the reforecast to forecast task, as in the EUP bench data, we have to think a bit more careful how to do this because we have 51 members in the training data, or other way around. We have 11 members in the training data, 51 members in the output data. And this means we have to do this sort of batch-wise. So we process batches of 10 and then one 11-member batch to better match the ensemble size between the reforecast and the forecasts. So that's how it looks if you put all these pictures together that I showed you. That's the full model architecture. I will call this full model architecture the graph attention model, or GAT for short. We looked at some sub-versions of this model to figure out like which of these parts is actually important for the performance. So we'll have one summary model where we don't use this member by member structure. We just do this as one single graph that uses summary statistics from the ensemble members. And we have a pure deep set architecture, that's what DS stands for, where we don't have any edges in the graph. We just have self loops at every single station, but there is no information flow between stations, just to figure out like what part of the architecture is important for performance. So here's a short overview of the hyperparameters, and you can find out more details in the paper that is linked at the end of the presentation. But just to note that we have lots of hyperparameters, and the models are fairly complex to train, so we did not fully optimize everything in a systematic manner, especially the distance. As I told you, we just picked 100 kilometers as a threshold. So one might do also better in terms of choosing hyperparameters. So that's the one slide summary of the results. A lot of numbers in one table, but the top half is the reforecast to reforecast task. The bottom half is the reforecast to forecast task. We have 3 blocks for the 3 different lead times we consider. We have the CRPS, and then we have the length and coverage of prediction intervals. Now I want to highlight here the CRPS results. So that's the raw ensemble. Then we have DRN as a non-graph based neural network benchmark. And you can see that the graph neural network models consistently outperform DRN. In terms of magnitude, these differences are not huge, but they are consistent across all lead times. If you look at the versions of the graph model where we removed some parts, you can see that we do no longer really get any consistent improvements. For example, this like summary-based model typically does like a little bit worse or only minimally better than DRN, and also this pure deep set architecture, which doesn't use a graph, typically does worse or only slightly better than DRN. So having all these components available seems to be important for really being able to improve over the DRN forecasts. We also looked at sort of pairwise significance tests to figure out if these differences are small in magnitude, but still statistically significant. So we used some t-test based procedure. I just want to highlight here the comparison to DRN. So the numbers here mean that if you, for example, look at these 30%, means that in 30% of the stations, we observe statistically significant improvements over DRN. And the number on the opposite end of the table means that in 0% of the station, DRN significantly outperforms the graph neural network. And if you look at this over the lead times, you can see that the improvements or the number of significant cases gets smaller, and in the end, we may only end up at like 10% stations with significant improvements over DRN. We also looked at like which of the input features are important for the models. And this is a little bit as you would expect. So the temperature forecasts are naturally the most important inputs to the model, followed by this maximum and minimum temperature forecasts, which get more important for longer lead times, which I think is also what you probably would expect. And yeah, lots of the variables only show like a minimal contribution to the overall performance and don't really seem to matter, and the model seems to ignore those largely. So that's just for the reforecast to forecast task. You can see the same illustrations for the other tasks and lead times also in the paper in the end. Now, trying to summarize and discuss this, so what you've seen is that we propose a GNN model that enables now information sharing across locations. We achieve consistent, somewhat significant improvements over DRN, and it seems like all of the different components seem to be important for actually achieving these improvements, especially this attention mechanism. Now, one question that came up in lots of discussions over the past days is that, like, does this now mean that we should only be using graph neural networks for post-processing now? And I don't think that's the case, so probably not. But I still think that they are an interesting choice because they allow to do things that you weren't able to do before. So incorporating new aspects to post-processing, but as someone interested specifically in more methodological questions, I think that there are also new interesting questions that come up. For example, I think it would be very interesting to try to find out what these models actually learn. So can we maybe try to find ways to figure out how does information actually flow from station to station? Does this have any sort of metrological interpretation? Or the other way around, can we use metrological knowledge to better build this into the design of the graph? So can we somehow build in some flow directions conditional on the current weather situation? And one thing that I wanted to highlight here as a side note is that this is one of the few instances that at least I have found in the work that we have been doing, where having the full ensemble as an input is actually beneficial compared to just using summary statistics. So I mentioned this paper by Kevin Höhlein, where we really worked hard to develop architectures that are permutation variant and try to really use the full information contained in the ensemble, but we failed to achieve any consistent improvements over just using summary statistics. But here, this seems to be a case where having the full ensemble really matters, and I would like to understand why that's the case. So to conclude, as next steps, so one thing that we would like to do is to extend this also to gridded domains. You've seen that these graph neural networks also work very well for gridded domains in the GraphCast or these Meteos with Nowcasting applications that you've seen. We just considered graphs built up of spatial locations, but you also have a temporal dimension, so you could also do this temporally. We could also link stations over time, over lead times, over forecast initialization times, which makes the models arguably more complex, of course. We want to think more about how to construct these graphs, not just using simple distance-based metrics, but you could also connect stations if they are similar in some suitable sense due to their metrological properties, maybe what you would expect. And we want to look more into where do these improvements actually come from? Are there certain station-specific effects or metrological factors, things like seasonality, which we haven't really done yet. So with this, that's the reference. So the paper has appeared as a workshop paper at this year's ICML, but you can find it on arXiv. And with this, I thank you for your attention. I'm happy to answer questions.
Many thanks, very interesting. Any questions? Yeah, Jonas.
Is there a way that we could produce predictions everywhere with a graph-based approach on stations?
Not in the way we did it. I wouldn't know how to do this. I mean, you could do this on a grid and then interpolate from the grid to stations. But here you rely on building the graph at the locations where you have the observation, where you train your model. So,
all the learned parameters on the nodes, on the vertices are sort of specific to the network. They're not.
Yes, I mean in our application and in our implementation, yes. There might be variants to do this. So you could also maybe learn some sort of latent representation, have a separate decoder that then maps back to individual stations that are somehow not part of the locations where you train this, but you will still need some training data at those stations, so you can't completely do this out of sample, I would assume. Not in the way we implemented it, but I would not, I'm not an expert on graph neural networks. I would not exclude the possibility that there are architectures that do exactly this.
Thanks.
Yes.
Thanks for the talk. I have a question about, is it very stupid to think about extend the graph also inter-parameters, so not in space and time, but between parameters, because I hear it's always an issue, the inconsistency between parameters.
Yeah, that's true. That would be another way to extend this. So you could have like multi-parameter, multiple temporal resolution, multiple stations. At some point, I guess you will run out of training data to then fit these models. This was already here, I think, some issue with the EUP bench data where you just have like 2 years of forecast data or 20 years of these sparse reforecasts. Yeah, it would be interesting, I think. Yeah, I agree. Also, yeah, one thing that I think it's on the slide, but I forgot to mention it. It's like, so we just produce distributions as output. You could also produce members as output, which also would help to possibly ensure consistency then in different variables, in different multivariate scenarios across space and time and variables. Yeah.
Okay, thanks. Can I have a short other question? It seems very appealing in this method that already the AI-based, data-driven forecasts are also based on graphs. Some of them, like GraphCast. And is there anything against it that it could be so the post-processing step could be unified actually with the whole prediction step? So additional to the reanalysis that it's trained on, already train on the stations and then in one go do the same job, or is it something?
Yeah, that would
realistic?
be interesting. I think that's one of the developments that is certainly ongoing in terms of developing these data-driven models. One question is whether you will need any post-processing after all, if thought of post-processing is part of the model already. I think I have no magic glass ball that tells me what will happen, but this might be one of the things that companies like Google will be working and looking at how to train models also from observations. And then it will be interesting to see if there is still some benefits to be gained by post-processing for then specific applications, specific locations, for example.
I think you wanted to go first.
There are ways to combine station data with satellite-derived profiles, and it might be interesting to look at the retrieved satellite-based parameters and combine them with station data for, nowcasts for areas where there's no station data. So something to consider.
Yeah, certainly. I think that's one of the things that is certainly going on when people are thinking about how to train these data-driven models, fusing station information and other types of information.
Yeah. Thank you for the nice talk. I have a question as well. And the baseline model you compared it to, you put out a Gaussian distribution, right?
Yes.
How do the distributions look like from the graph neural network? Did I miss this, or?
Yeah, they are also Gaussian distributions. So the node level output are parameters of a Gaussian distribution. So they are also Gaussian. I mean, there has been lots of debate about this. I think for temperature, using this Gaussian assumption is fine. I did not really talk about the benchmark model in much detail. There are alternatives, like there is John's BQN model, which does this in a much more semi-parametric, more flexible way, where you don't have to assume a Gaussian distribution. In many things that we did not find that much of a significant difference between assuming a well-suited parametric distribution versus doing something more flexible.
Yeah, because I'm asking, because if you have a Markovian graph, like a random graph, and you fulfill a Markov property, you always get Gibbs distribution. And so with the Hammersley-Clifford theorem. So I was wondering if this could be a case where this applies.
I mean, certainly you could do differently, and that you could get a different type of output. That's what I meant. Also, you could not generate a parametric distribution as an output, but you maybe have some ways to generate members as an output, which is something we want to look at. We here just followed what we did earlier and simplify the problem by having this parametric distribution as an output, which also allows you to train the model and using the CRPS, because you get a closed form solution of the CRPS and can like optimize the whole model parameters jointly.
Okay, thank you.
Marcus has his obligatory question.
Thanks for finding time for me. As far as I understand it, the biggest advantage should be this interconnection between the stations now. And as far as I remember from the benchmark, there were verifications where there was a clearly advantage at coastal sites with different methods and so on. But you now artificially cut this, you had this D, which was some kind of radius. The reason for that, I guess, is computationally, or?
The reason for this was that we just didn't have a good idea what to do. I mean, in principle, you could also, the one idea we had in the beginning was to start with a full graph where everything is connected to everything. But this makes the model, of course, much more complex because you get much more parameters that you need to learn. So we thought we need to sort of restrict this in some meaningful way. And we thought like one way to do this would just be to take like the local environment of a station, which is very likely not the best way you do this. And that's why we want to look at different ways to connect this. I think, yeah, it might be interesting to also go back to this idea of having connections everywhere and learn, have the model learn where the important connections are. But I'm not sure if that's computationally feasible. So that would be something we have to look into.
And follow up on that, also from the benchmark, Peter clearly showed there is an advantage of using different lead times as well. But I guess that's the same reason, no? It's too expensive then to run also in time these connections, right?
That's something that we have tried to use across lead times and also across model runs to have these connections. The problem is that the models also there get much more complex because you again get much more connections and then how do you connect all the members at the different stations across each other across lead times. So it's we tried this. I think maybe the benchmark data is not the best suited data set for doing this. Also because of the reforecast, if you train, you have these like sparse initialization times. If you move to the forecast, you have daily forecasts. So it also there's a mismatch between those. So we tried this out a little bit with not much success. Maybe with a different data set that might look different and more data to train.
Okay, thanks.
And whenever you connected two stations, did you only consider the horizontal distance, or did you have into account also the altitude? Because perhaps some stations that are high but far away can be more related than some stations
that
are closer.
We just considered horizontal distance without any accounting for the altitude. Yeah, I think that sort of this like design of the graph is one of the things where you could potentially improve a lot by using things like altitude categories and connecting those stations, or just finding some sort of measure of similarity between different stations in terms of their properties of forecast errors or observations. I think this could improve a lot. We just didn't have time to try it yet.
Okay, and just a short question, you mentioned that using the ensemble members plays a role. And is this because you used an statistic out from the ensemble, like the ensemble mean, or did you also try with the median? I'm wondering about the spatial structures, that if you use the ensemble mean, you destroy those structures, but using the median, this is avoided?
So here, our model proceeds sort of member by member wise, and we looked at a model that has summary statistics. We just used the mean and standard deviation. We didn't look at other summary statistics. But there is this Höhlen et al. Paper where you can look at and find more about our efforts to use the full ensemble information in a different context where we didn't succeed of getting any improvements over just using summary statistics. So it would be interesting to find out what matters here for the graph neural network model, why that's different here. I don't have an answer.
So thank you, Sebastian, for this very interesting presentation. And I have a question which I think was already somewhat implicit in the other questions, is that there's a lot of things you can do with these architectures, like so many interesting things you can try, but it seems that it is somewhat limited by the data we have available, right? And you are always walking this line between overfitting and then trying something new that can be more expressive and then hitting that overfitting wall again. And I was wondering, what is your opinion on what strategies are you, when you are designing, let's say, an architecture, what are you thinking about how to like, how do you prune your ideas based on the data you have? Is it like, are you thinking about, okay, maybe I'm going to regularize this, or maybe I'm just going to have it more bespoke, more like specifically tailored, or I'm going to try some data augmentation? Where do you see the future going if let's say that that we do not get, that the data doesn't scale as well as our ideas, basically?
Yeah, I think that's a very good question. I wish I had a good answer to this, but I don't. I mean, especially in this project, this was a lot trial and error based, because this was also the first time that I worked with the graph neural networks, that the student worked with the graph neural networks. So it was a lot of figuring out how you can actually implement things and what works and what doesn't work. So this was very experimental. And you end up with, as you said, so many ideas and so many things you can try that you also just, the computational resources that you have available very much constrain of what you can do with this. Yeah, so I don't have a good answer. But I think that's a very important point for going forward and also developing AI-based post-processing models or forecasting models.
Maybe the last question, or because we run out. Fine.
I was just thinking, have you considered DRN, comparing with DRN with some spatially compressed information with an autoencoder?
We haven't, but that's another thing that would be interesting to try. Yeah.
Thanks again, and I think we have to proceed now. Next speaker, Siet Ben Beloage, with evaluation of machine learning models from forecast verification to model falsification. So, thanks.
Thank you, Alexander. So it's very hard to first, thanks to the organizer for having me here and for giving me the other opportunity to talk. And it's, I think, very hard to come after two very good speakers. So I was considering just playing my favorite playing list and dancing for 30 minutes. But I rejected this idea, actually. So I'm Ziad Ben Boalek. I'm a scientist at the European Center. I'm part of this AIFS team. So this is a group of people working toward the development of this AI-based forecasting system. So it's people from actually different departments, different sections, and different actual team at ICMWF. So I will not talk so much about AIFS here, but rather my talk is about evaluation of ML models. So the question I will try to answer is how to evaluate ML models. And the underlying question is, can we continue business as usual in this community in terms of verification? So there is already a hint about my answer to that question in the title, because I will talk about forecast verification, but I will try to elaborate on the concept of model falsification. So I think the first time that I give this talk, so please bear with me. So to set the scene, let's say this is a game we used to play, and we played here on Monday. So we have two forecasts. One is from an NWP system, the other one from the AIFS, and the question is, could you guess which one is which one? So this is the kind of game we play at the beginning, and so the AIFS is running, in an experimental mode, but routinely for more than a year now, actually. And you can have a look at the forecast on our website. But we have also now the first ensemble version of the AIFS. This is so-called the diffusion version of AIFS. And you have plots as well on EC charts, and this is more recent. We started sharing this at the beginning of the summer this year. And if you go on our website, you can look at more than AIFS. You can more ML models, and so very on in the process we try to engage the community, so to make this forecast available to it's a maximum of people interested into that, so that anyone can make his or her or their own opinion. I think this is kind of step 0 in the evaluation process. So to visualize, to have an eyeball check of the forecast, and so so what you can I mean, the list of models you can have access to at the moment is, so if the AFS, you can access the data as well, not only the plots. We have ForecastNet, we have Fuji, GraphCast, and Pangu Weather. And behind this model, there are different teams from different institutions, and there are these papers, if you want to know more, so from Lang, Patak, Chen, Lam, and B. So while preparing this slide, I thought, what if we apply induction, so an inductive reasoning to this slide? So we will try to generalize from this small sample. So and one generalization we can do. So this is the type of process we use in machine learning, right? Induction. So one generalization would be that if you have a short family name, so if you have 4 letters or less in your surname, you have more chances to write a big ML paper. So I will come back to this idea of induction, right? Which is at the heart of the machine learning process. So accessing the data, I think is very important. I mean, for the community as a whole. I mean, if we want to have PhD students looking at the forecast, to dive into them and try to understand the pros and cons is very important to make this forecast available. Not only the plots, but also really the data. So one can compute statistics. So, I mean, too much knowledge at the moment. There is 3 places where you can get data. So it's TSMWF from Mars, from our archives. So where the machine learning models are initialized from the IFS analysis. So this is real time. And there is a number of models that we run, but if you are not part of the member state, you will only be able to access the AIFS and not the other models. Another way to access this forecast is to look at the Weatherbench 2. So this is a Google DeepMind initiative with Stefan Ras in the front line. So there, the forecasters are initialized with ERA5. They are mostly reforecast, so if you are interested in more recent events, you will not find them. And you have a limited number of models available there at the moment. The third option would, I mean, this is an initiative from the US, from Colorado State University and together with NOAA, where they initialize the forecast from GFS. They run real time. There is a visualization, and they are building a data set, an archive as time goes by. And here again, you have a subset, I would say, of ensemble. There is a last option. You can run the AI model yourself if you like. It's what Baudouin and Raoul developed at TSMWF. So if you really want to, you can build your own data set. But I think this is much more effort. Okay, so once you have access to the data, you can do a lot of analysis, different things. And I think we were kind of one of the first to do that, at least to look kind of independently at the performance of the ML models, independently in the sense that the group of people that developed the model and the group of people that did the verification are from 2 different institutions. So in this BAMS paper, we look at various aspects. So we initialize Pangu Weather from the AFS. We were in a kind of operational-like setting. And we look at various things. So of course, scores, but also at the characteristics of the forecast, like bias activity, smoothness. Look at case studies. So we run if you like, the verification and diagnostic tools that we had in-house. And so we didn't put everything in the paper, but a number of interesting aspects, I think. And one of the headline figure is this one, where you see in red the if you like the improvement over 2 decades of the NWP system. In black, the frozen version, the ERA 5, so we can see the year-to-year variability in the score, and then the jump really in quality with Pangu. Quality as measured here in terms of anomaly correlations. So yeah, that was really the headline figure of the paper. So I was quite pleased with myself and the work we did with the group of people for that paper. But the feedback that I received, I mean, a number of times is, yeah, very nice, but what about the forecast realism? I had the impression we touched upon that question in the paper, but that's a question that came again and again. So the first thing I did is to check in a dictionary what is the definition of forecast realism, and I find this interesting one. So realism is the quality of representing a thing in a way that is accurate and true to life. So I found it really, really interesting. I mean, the interesting part, I would say, is that it's not just about, I mean, realism is not just about accuracy, it's about something else as well. So there is another component to realism, not just accuracy. So I think it's a good time to have a short break and have a sip. So you can think about what is true to life. So okay, so I came with this proposition here that one way to evaluate ML or data-driven models, I mean, is to do it in 3 steps, considering 3 types of realism. So the first step would be to measure forecast performance. That way we'll measure the functional realism. The second step would be to assess the characteristic of the forecast. So that is related to the structural realism. And the third step is testing the forecast trustworthiness, which is related to physical realism. So this is basically the outline of the rest of my talk, and that's how I will go through these three aspects and try to develop with examples. So let's start with the functional realism. So the question here is the forecast fit for purpose? So on one side you have a forecast. Let's say it's your object, and then you have your task, and you check whether this object is fit for your task. Of course, you can have several objects, and maybe object A is better than object B, so you can rank which one is better for a given task. So this is typically what is done in forecast verification, and you can do it more qualitatively with case studies. So the first example here is a study by Jin and al, people at Microsoft Research. So in their paper, they are promoting the use of CNOP observation, or not CNOP, but in situ observation, let's say. They call them real observation, in contrast with using analysis as reanalysis as a truth. And they emphasize the practical value of the model for given application. And they say we need to somehow assign a task to a forecast, so then it's rather easy to evaluate this forecast. And eventually what they did, they compute the root mean square error as a function of the lead time, and they show that Aurora, the model developed by Microsoft, is number 1 in this metric. So that's the way they did it. So this is the kind of the very first step. Now you compute the root mean square error. But of course, we know in this community that weather forecast is also very much about anticipating extreme events. So there is a lot of interest in there. And this is, I think, a very nice example by Linus Magnusson in SMWF newsletter. So this is a case of unprecedented rainfall in Dubai. So maybe you remember the picture in the news of Dubai airport completely flooded. That was some time ago. There was other extreme event between there and now. So and here this is what we call a forecast evolution plot. So we look at forecast initialized at different time, but all valid for the same point in time. And the event we are looking at is the event marked by this, let's say, purple cross. That's the observation, around 150 millimeter in 24 hours, which is 5 times bigger as the maximum ever seen in the reforecast. So it's really completely out of the climatology, local climatology for that time of the year. And we see that, nevertheless, all models, so we have various models here, so NWP and AI models, also the ensemble, the AIFS ensemble, but they all kind of pick up quite early, more than a week in advance, a very strong signal that something very unusual, so above the maximum in the climatology could occur on that day. So very good, I would say, predictability for that event, a very good performance from all the models, including the AI ones. So this is a way to look at extremes, so looking at case studies, but you can also compute scores, and of course for extreme it's better if you have a probabilistic view on these things. And this is a plot from Price et al., so the people that developed GenCats, so people at Google DeepMind, and ensemble AI model. And what they are looking at here is the potential or relative economic values. So if you know which kind of threshold you're interested in, and so for the different rows you have a different threshold, and for the different columns you have different forecast lead times. And if you know your cost-loss ratio, then you can know exactly what is your the potential or the economic value of your forecast. And in this example, they use this metric to kind of highlight that GenCast is better than the ensemble for this kind of decision, let's say. So this is really the first aspect, the functional realism. So the second aspect, which is also important, is the structural realism. And here, the question we ask is the forecast consistent with the observation? So we have a first object, which is the forecast. The second object is the observation. And then you look at the characteristic. Do they have the same characteristic or not? And maybe you can dig a bit further and try to understand why they don't have the same characteristic. So for that, basically, we use a diagnostic tool, reliability analysis, and case studies as well. And to stay in the field of kind of looking at extreme or high impact event, this is a study by Pache and al, where they look at compound events. So where it's important not only to have one variable right, but to have the combination of one or two variables together to get the right impression about the coming high impact event. And this is an example for humid heat waves. So as you can guess, not only temperature but humidity was also important to forecast this right. And they try to figure out whether the nonlinear combination of the predicted output could reveal some weaknesses in the ML model. But at the same time, they look at extreme events, and so they have this nice plot where you have, as you can see, several distribution of the heat index, and so they compare distribution, and as you can see, the AI models tend to underestimate really the extreme in this occasion, which is not really a surprise. We know that ML model tend to smooth, so to blur, especially with increasing lead times. So forecast smoothness is one characteristic which is important to diagnose. So the question whether there is a lack of granularity really in the forecast from ML models. So one study, which nicely show that is the study by Massimo Bonavita at SMWF, and he used Pangu weather as well, and he showed this so power spectra So where we see the energy as a function of the wavelengths, and so and we clearly see the reduced variability at smaller spatial scale, in particular at longer lead time. So another way to look at this granularity or smoothness of the forecast is to compute the forecast activity. So here we have just one number, so there is no decomposition as a function of the scale, so it's just one number, which is computed as the standard deviation of the forecast anomaly. And so we can plot the activity as a function of the lead time and to see whether we have some trend. So as the forecast progress, whether we lose granularity. And so this is one aspect, the activity. But as we know from the math, actually, if you write the math, you know that the accuracy is very much related to the activity. So there is a link. So you can check whether activity and accuracy are related, and this kind of plots are available also on EC chart, so you can have a look at the forecast, but also at the scores. But it's somehow difficult to go back and forth between these two plots and to ask yourself which one is more important. So we had the idea to actually have a plot where we show the two aspects in one go. So in that plot here, we show the delta activity and the delta accuracy. So I will try to explain a bit better how to read this plot. So the delta accuracy is if you like, the improvement with respect to the IFS control forecast. So we call it control, or previously it was the high res. So if we are better than the high res, we are above the zero line. And then we look at the activity and we compute the delta activity with respect to the analysis. So do we have more or less activity? Are we smoother or not than the activity? And if we are on this side of so on the left of the plot, it means that the forecast is smoother. So we'd like to draw your attention on the red line first, which is the result for the ensemble mean. So we start with the day one, which is close to zero, where all the forecasts have more or less the same activity and the same accuracy. And as forecast lead time progress up to day 10, we see that the ensemble mean start to be much better than a deterministic forecast, because we wash out the unpredictable scale, and this washing out result in a if you like, in a loss of activity. So the question is whether ML models behave somehow like an ensemble mean, and we see that it's possibly the case for Fuji, which has very much the same behavior here. But for other forecasts, other models, sorry, like the IFS and GraphCast, we see that we have quite substantial improvement with respect to the IFS, but with for limited deterioration of the activity, really. So this is a way to see, to realize that there is a relationship between accuracy and activity, and to think about the trade-off between these two aspects. So functional and structural realism are also somehow related. Let's go to the third, maybe the trickiest one, the physical realism, right? So the question here is the forecast trustworthy? And we will use here a method called model falsification. We look into that, and here again, I think case studies are really, really important. So we'll try to elaborate on this concept of model falsification in just one slide. So to come back to this idea of different type of logic, so the deduction, the deductive logic is generally applied when you have a NDP model. So we have rules, so the law of physics, if you like, and we have initial conditions. So if you have the data and if we know, or we think we know the rules, then we produce a forecast. So this is how deduction works, I would say. In a ML context, we are rather using induction, where we have data and the answer on one side, and what we have as a first primer output is a new set of rules, actually. So the first output of an ML model is not a forecast, it's a new set of rules that are encapsulated in what we call weights or checkpoints, and that that actually describe new theories in a sense. So if you like at a bit at the history of science and the way to confront new theories, is a standard method is falsification. So the standard method to evaluate not the forecast but the theory themselves. So the primary output of the ML model. And so it's you can see it as an attempt to refute the theory. So the idea is really to find the limit, the boundaries of the application. And so the real verification is only when the refutation fails. So when we try to push the limit and we see that it still works, and we are happy. And I have so this idea of falsification comes from Karl Popper, actually, from the last century philosopher. So one example of trying to push the limit, and people didn't broke really the system, is the study by Hakim and Massana at the University of Washington. And so what they did here is a physical test where they use different models. They use GraphCast and ForecastNet, and they apply so disturbances to the field, and they look at how it evolves. So this is I think panel A, B, C, and D, and so the propagation of the signal is constrained by the dynamics. So they wanted to check whether the results is coherent with the knowledge of the physics, if you like. And they conclude that the model encodes, so ML models in that instance encodes realistic physics in all experiments. And this was the case for one of the models and not the other ML model they tested, actually. So they were quite positive about the idea that there is some physics encapsulated in the ML model. So another so falsification study, in a sense, is this ablation study by Kian-Soon et al., where they had the idea to test the system if they remove from the training the most extreme event. And they were interested here in the tropical cyclone, so they removed category 3 to 5 tropical cyclone from the training and check whether, without having this kind of event in the training, if the model was still able to forecast well tropical cyclone. And they find out, not sure it's a big surprise, but it's not working much less. We see a clear degradation if there is no such event in the training. So they have a test experiment where they remove also 25%, but randomly from the training. So they reduce the size of the training to check whether that was not the main explanation for this degradation in the forecast. And so they conclude that AI weather model will produce unreliable early warning for unprecedented weather events, what they call a gray swan. And I have a third example of what I would call really falsification studies. Is this case study of the storm Charan that was performed by Sharton Perez et al. At the University of Reading. So they had really a close look at this particular case. So one storm in particular, and they had a detailed really analysis of the physical structure of the storm. And this is just a picture of the different, showing the different model they use for the study. And they conclude that only some machine learning models resolve the warm core seclusion, and none of the machine learning models capture the sharp bend back warm frontal gradient. And that tells me that I still have a lot to learn about meteorology. But the interesting thing is that they actually compare the forecast with their knowledge. So this is the idea of the physical realism. You have the forecast as an object, you have your knowledge, and you want to see if the two fit together. And with that, I come to my summary. And so, again, the idea is to approach the evaluation of ML models in three steps. The first one being to check the functional realism. So, is the forecast fit for purpose? Traditional forecast verification, I would say. Second step would be to look at the structural realism. So, is the forecast consistent? And it's what people are doing in diagnostic. And then a third step to look at the physical realism. And the question being, is the forecast trustworthy? So to try to find the limit of application, and that would be related to model falsification. So, and to conclude, I would say that very happy to be here, and thank you very much.
Many thanks, very interesting questions. Yes.
Thanks, yeah, very nice talk. I was wondering about the tools for different goals you defined. So where do you see is the biggest lack of available tools to assess these different aspects of realism?
Maybe it's not a surprise, but I would say number 3 is very new, in a sense. I mean, in our field, maybe not in general, but I think there is a lot of space to develop ideas. Forecast verification, the number one, there is so many tools that have been developed for NWP, so I think we still need to use some of these tools to evaluate further the functional realism of the ML model, structural realism as well. I mean, the reliability aspect, the bias, etc., is something that we know how to look at that, and we have a lot of tools. Physical realism is really one that need a new, maybe fresh and fresh ideas. Yeah.
Thank you very much. Very, very, very interesting. It was really amazing what you did on that. Just concerning the smoothing of the machine learning techniques, is it related to the resolution of the data you are using or not?
Yeah, I think this is really part of the diagnostic, right? To try to we see that there are differences in terms of characteristic and trying to understand what does that come from. So resolution is one aspect, I think, but maybe not the only one.
Do you think if you increase the resolution of the let's say the reanalysis data, we will improve that or not? What are your expectations?
I can come back to this to the plot. You mean this plot?
Yes.
So Aurora is one which is at the 9 kilometer here. So it's a higher resolution model, but still it's smoother than other ones. So it's a matter of loss function as well. So it's different thinking there. Mm-hmm.
Also from my side, thank you very much. I would have a follow-up comment, question on the first question and on your answer. I understood that for the physical realism, you were talking about the falsification in the sense of Popper and I mean, I thought that the whole framework of hypothesis tests is basically doing exactly this. I mean, I don't say that there's no room for improvement, but there is a very well-developed tool set that exists, which exactly does this job on a statistical basis.
Could you develop? So which job exactly do you mean?
I mean, the basis idea of a hypothesis test is that you formulate a null hypothesis that you suspect to be true, and then you reject it at a certain level of significance, and then basically you falsify it at this level of significance. So this would be the reasoning. And I don't know if this is exactly what would fit the purpose, but I just wanted to mention this. This is maybe goes in this direction.
Yeah, I think sometimes it's more on the knowledge level, and it's harder to quantify. So we have accumulated a lot of knowledge about the atmosphere, the Earth system, etc. And so we want to know if this, what we see in the forecast that are the output, I mean the way to understand the knowledge or the new theories encapsulated in the ML models. So whether these models, I mean, whether these forecasts they match our understanding of the world. So I think it goes beyond just testing hypothesis as you mentioned. But
I agree. If it goes to physics understanding, then it's not the right framework. I agree on this. Thank you very much.
Any more questions? Yeah.
Thanks yet for your talk. You know, and I know that we are matching a lot of ideas. We are matching on some points. To comment what Sebastian said, there is a very simple way to test physical realism. It is just to make a kind of Turing test. Well, and this is the kind of game that Zied talked about before. You just have to compare one physical model output and one ML model output. Just give maybe 10 or 20 points to a on-duty forecaster, and he or she have to spare these points among the two forecasts. This is the very simple way to ensure trust, because we are all speaking about web application and forecast output, automated weather prediction, and ML model are very well suited to make all these duties, but finally a model like ML models, are they very useful for severe warnings or warnings at all? If they are still human induced, I don't think so. So I don't think this is the end of the world as we know it, to be honest. So at least, yeah, it depends of what you want. Maybe, and in more and more national center, this is not the case. We do not care about physical realism because we do not care about consistency, unfortunately.
Yeah, if I can respond to that. The thing is, I mean, what I was trying to say is also very much about being honest about when does the system fail. So really to be clear about the limits. So to have not only like success stories, but also to have failure stories in the landscape. So I think this should be important, I think.
Thanks for the nice presentation. If you go back to the figure with the activity and the variability, yes, it would be nice for me to show also where you have that activity, not really the standard deviation of the forecast anomaly, but the number of clusters. So in a sense, it would be interesting to see if your machine learning model is able to reproduce different realities, not in terms of spread, but in terms of real trajectories that is following, right? Because that could be the real problem. If the machine learning is predicting, is too sure that the future will be that way, that can be the problem in the spread, right? Maybe the traditional forecast is able to figure out different trajectories, while the machine learning is overconfident over just one. So, so in terms, if instead of standard deviation, the number of clusters, or that would be interesting to see. Just a comment.
Yeah, but here we are not in the ensemble world, so maybe I was too quick here. Those are the deterministic models. So And the standard deviation is really measuring the smoothness. It's a measure of the smoothness, whether you have high variability in your field or if it's always very calm. And so yeah, which is kind of a drawback of most of the forecasts. So, yeah.
Thank you for a great talk. We are all really involved. I have a question also related to accuracy to activity relation, especially for longer lead times. In my opinion, there is one statistical point of view that was actually we were struggling with even when going into higher resolution models when compared to the models with the coarser resolution, because you would get more details and then you're more prone to double penalty, etc., etc. But what I have figured out, at least it's my personal opinion, that if we go too far in the future and we lose the accuracy, for me it might be even more natural to see something fuzzy than all the details that could be somewhere else, and especially once we move towards the ensembles and probabilities. And then maybe in some next step maybe go back to the details. But for me it's a real question whether the fuzzy as itself, I don't know, 2 weeks ahead is such a bad thing, because yeah, maybe we should have another way of expressing the spatial variability, but not just drawing the details, which are probably not where they exactly where should be, if you can understand what I mean.
Yeah, I think that's why I wrote sometimes it's an undesirable characteristic, but sometimes people like to look at the ensemble mean. That's what they need for the application. But if you would like to have a realistic scenario, so in all sense, then you would like to have this realism across lead time, just not for the first days, but and then you can build an ensemble, and from the ensemble you can derive the mean, you can derive anything of interest to you, I think.
Any other questions? Marcos? Not this time? Yeah, for sure.
As you said, there's every other day a new paper, new model, and it's getting more and more complicated for weather services, but also individual people to follow it. Could you see ECMWF a little bit in responsibility to be the AI police or write the best practice or best, because I'm missing that a little bit at the moment.
I will pass your comment to my managers and we'll see if they are happy to be the police in that field. I don't know. I think, yeah, I mean, just I think that there is a need to really to make the forecast available to everyone, and so anyone can not only look at the forecast, as they said, but do the statistic, play with the forecast, the data, but also the models, and I think this is maybe somehow surprising, because even Google, Microsoft, everybody start to put their model out there, and people can use them. So, which was not given at the start of all these stories.
Is ECMWF, for example, planning to include such tools like this activity accuracy thing into Anemoy, or is this planned to?
Another good question that I will report to my supervisor. I think not at the moment, but.
Okay. Any other question before we move on? If not, then thanks very much again. So the next final talk before lunch break, and the final talk for today, in fact, is about deep learning-based post-processing model for thunderstorm occurrence using vertical profiles from convection resolving ensemble forecasts by Kianush Wahid Yousefnia. Sorry for my pronunciation.
Perfect. Yeah, thanks. Can you hear me? Is this working? I feel like a TV weather guy.
Yeah, it should work.
Let me just put up a clock here so that we all can go to lunch in due time. So hello from my side. Thanks for bearing with me and keeping up the concentration. I have a machine learning model to offer and hope that it will not falsify it directly. So the idea is to identify thunderstorm occurrence in NWP data. And since I'm from DLR, and so from the German Aerospace Center, I feel I need to motivate the subject with aviation. I think, so this is from flight Austrian Airlines 434 from June this year. I guess this is as close to a bloody nose as an airplane can get. So this people might have gotten, so the passengers might have gotten the fright of their lives in this aircraft, but obviously thunderstorms is not only interesting for aviation, also for agriculture, event management, and also like the entire general public have an interest of not getting struck by lightning. And so if you do want to do a thunderstorm forecast with a lead time more than 1 hour or 1 or 2 hours in advance, there's currently no alternative to using NWP. And the way to do this is that traditionally we look at certain atmospheric variables from which we know that they are correlated with thunderstorm activity. So for example, we might look at model radar reflectivity, or we look at CAPE, column integrated grapple, etc. And then either a meteorologist looks at them and infers thunderstorms from them, or we have an expert system or machine learning. But if you think about it, CAPE, for example, can be computed from knowing the vertical profiles of temperature, pressure, and specific humidity. So these features that we have been traditionally using, they derive from vertical, or at least most of them derive from vertical profiles. And so our idea was to replace this middle step completely and go and train train a machine learning model that directly takes the vertical profiles from NWP and infers the probability of thunderstorm occurrence from them. The model, for that reason, we developed a model that we call Salama 1D, and I would like to show you in this presentation that using vertical profiles directly leads to a model with that outperforms this traditional way of using signal-based features, and I will show a way of understanding what the ML model does internally and how we can interpret what's happening inside the model, and perhaps even shifting from this black box prejudice of machine learning. And just to be sure, so this is a model for inferring patterns of thunderstorm occurrence in NWP data. Now, to really use it to do a thunderstorm forecast, for example, let's say we want to know 5 hours in advance if there's a thunderstorm over Berlin, for example. Then in order to use our model, we still need the NWP forecast 5 hours in advance. So we need the vertical profiles 5 hours in advance, and then we can apply our deep learning model on that to get the 5-hour forecast. And we train the model in such a way that we use the same model for each lead time. So we actually train the model on lead times, on small lead times for which we expect NWP, the NWP profiles to be quite realistic. And then we will, it is part of this presentation, I will show you how skill of the model then depends as a function of lead time. Okay, so let's see how this deep learning model looks like. So we use high resolution a high resolution NWP model, so IconD2, the APS version of it, and we use basically all full level fields that are there. So there are 3 wind components: temperature, pressure, cloud cover, specific humidity, and the mixing ratios of cloud cover, graupel, and ice. And we use all these field atmospheric variables on their native vertical grid. And this is how this deep learning architecture looks like. So we start by 10 fields on their 65 vertical levels, and now we have an architecture that reduces dimensionality to over mostly dense layers to a single output, the probability or a probability of thunderstorm occurrence. So this is also a pixel by pixel model that we're training here. The most interesting part is here, this is what I'm calling a sparse layer. The idea is the following. So if I had so I am starting with a 650 dimensional input, and I want to go down to a smaller dimensionality. If I did this with a fully connected neural network, the number of trainable parameters would explode. And to mitigate this, so I do the following. So in a fully connected neural network, so this is my input layer, this is my first hidden layer. In a fully connected neural network, I would have connections between every node of the input layer and every node of the first hidden layer. But what I'm doing now is I introduce sparse connections. So these first nodes here connect only to a subset of the nodes here, and so on. It's very reminiscent of convolutional neural networks, but I'm not using weight sharing. So for each block, I have a separate set of weights. And on top of that, so we have here in the vertical direction, this is the height dimension. On top of using these sparse connections, I also shuffle these blocks along the Z dimension. This allows me, that way I promote the machine learning model to, I prevent the model from learning structures or patterns tied to the vertical grid structure. So by the model, now the machine learning model has to learn from the data at which height it looks at the moment, because now it can only, for example, by looking at the pressure profile, learn about how to orient itself in the neural network. Okay, now for training, as I said, I use IconD2 EPS data. I trained the model using 2 summers, 21 and 22, and as labels, I use lightning observations. And a pixel is identified as lightning if there's at least 1 flash of lightning within a radius of 15 kilometers and a time threshold of 30 minutes. And I do the splitting and training, test, and validation set. And my output, as I said, is a probability of thunderstorm occurrence. So a number between 0 and 1. And by looking at a reliability diagram, I actually check that the output actually does exactly what it's supposed to be. So for example, if the model outputs a probability of a number of 0.6, it actually means that the probability of thunderstorm occurrence really is 60%. Right. Now that the model has been set up, I promised you a comparison to this traditional way of looking at high-level derived input features. The benchmark is a model that we have worked on a year ago and have been published in the quarterly journal. Call it Salama 0D. It's been trained on the same data set, on the same NWP model, on the same model domain, but instead of using vertical profiles, I use 21 derived input features known from literature. For example, CAPE, radar reflectivity, cloud top, cloud cover of high-level clouds, etc. All these standard features that are known from literature. And we trained a classic feed-forward neural network to infer thunderstorm occurrence. Here's a case visualization from an August day in 2023, which was not part of the training, where there was a thunderstorm over the Benelux region, so shown here in this black, with this black contour line. And now in red, I'm showing the probability of thunderstorm occurrence as was given by the model output. And as you can see, the benchmark produces a lot of false alarms in southern Germany, which is corrected for by on the right side by the Salama 1D version. But this is just one example. We also did a more systematic comparison using tests as a function of lead time with test sets compiled from the entire summer of 2023 using and actually we did this comparison for a wide range of skill scores. I'm showing here the results for the Breyer skill score, meaning the higher the score, the better. And you can see that using vertical profiles leads to an increase in skill for all lead times that we tested. So for lead times of at least 11 hours in advance. Now that we have this model, it would be interesting to understand what how the model treats these vertical profiles to come to a conclusion of inferring thunderstorm occurrence. Now for this, what I'm showing you here are so-called saliency maps. The idea behind saliency maps is that it's I'm looking at it is a measure of feature importance. The higher the saliency, the more the model looks at a specific feature. Now let's go into these saliency maps in a bit more detail. So in here, in these colors, I'm showing you the saliency for my 10 different fields. And you can see, you can infer the field of that I'm looking at by comparing the colors to the right panels. I'm coming to the right panels in a second. So for example, here, this is the saliency. This is the saliency of the U component of horizontal wind, and this is the saliency of the V component. This is the saliency of temperature, etc. And now I stacked the saliencies on top of each other, meaning it's only the width that's interesting. So that's the saliency of U. Then on top, that's the saliency of V, etc. This has the important effect that the envelope here is now a measure of how important each height is for the neural network. And I'm saying more about this in a second. No, and in the panels here on the right, I'm showing the average profiles for these different fields. And one last thing before we can go to the interpretation. I'm showing you here now this is the saliency map for the top percentile of my examples in my test set. So this is the average saliency that we get for those examples that have been assigned the highest probability of thunderstorm occurrence by the model. So in other words, this map shows us what variables and at which height the model looks at the most when assigning the highest probability of thunderstorm occurrence. Okay, now that we have explained everything, so as you can see, there are two peaks here. At least what stands out is a peak here and a peak over here. And this first peak corresponds actually to the tropopause. So the model seems to have learned about the concept of a tropopause. And the second peak here, we've checked, lies between the LFC and the equilibrium level of a parcel lifted from the mixed layer. And as we can see here, that in this peak, temperature and pressure is most important. This suggests that the model has learned about the concept, learned about atmospheric instability and at unstable lapse rates. And as we can see here, the violet part is relative or specific humidity. So the model is interested in specific humidity around the LFC, which, if you know about entrainment, we know is favorable to a thunderstorm development. Maybe here the pink part is also interesting, so that corresponds to the production of ice particles. Right below the tropopause, which suggests that the model specifically looks at ice particles to infer thunderstorm occurrence. And maybe one last thing: the fact that these U and V saliencies are quite high there suggests also that vertical wind shear seems to be important to the model, which is also confirmed by what we know from literature, that vertical wind shear can prolong the longevity of thunderstorm occurrence. So we see a lot of signs that do make sense when looked at them, and these are just some simple examples of how to use interpretability for machine learning models. And I do think that when we are able to at least understand in some sense how the model comes to its conclusions, then this also is important. This helps build trust on these models, and this is important when using those models in high stakes decision-making environments. I'm already coming to my conclusion. So this is Salama 1D, as I said, allows for interpretability. It outperforms a machine learning model based on single level predictors, and it allows for evaluations actually in real time. We built this model as a plug and play, and so it could be used, for example, by the DWD directly. And next step would be to actually process all ensemble members in one pass, and we'll see if that actually increases the accuracy of our Salama model. For this, thank you very much for having me, and I'm open to questions.
Many thanks. Very interesting again. Yes.
So how many model levels do you actually need? Could it be reduced by a certain number and still get the same skill in the end?
You mean NWP model levels?
Yeah.
Yeah, so we've been using 65. We haven't checked. We haven't checked that.
But do you think you can reduce it to, say, 10, and then you get more or less the same skill? Or because, I mean, you need to store all the data to actually make use of this. And that is maybe a problem, especially if you go into ensembles. And so.
Yeah, I mean, we need to store the data only for training, right? At the moment, we constructed this model really for the DWD to use directly. So that's why we construct the model in such a way that it's compatible with the model levels from ICON. But yeah, from physical point, it would be interesting to study this.
How long was the training period?
Do you mean
how many days or how many?
For actually the training of the model, one epoch took about.
No, I mean
minutes.
the training data set. What is the size
Sorry.
of the training data set?
2 summers of ICON D2, and we down process this to 400,000 examples. But yeah, 6 months in total, so 2 summers.
Yeah. Thank you for the nice talk. My question would be, what did you use for targets?
Yes, lightning data from the LINET lightning detection network, and the construction was then this is a pixel-wise model. So we are for deciding whether or not a thunderstorm occurs or not, we look at a single pixel, and now for the target as well as pixel-wise, and to decide whether for a given target, for a given pixel, whether there's a thunderstorm or not, we check if there's lightning happening in the neighborhood.
So it was at least one thunderstrike.
At least one flash of lightning within a radius of 15 kilometers and 30 minutes.
Okay, thank you.
Yeah.
Hi, thank you so much. It was a very nice talk. I'm just wondering if you can use the same model, because you said you train your model with 2 summer. Can you use this model for winter case, or you need to train again your model with 2 winter in order to have a thunderstorm?
So there's no one preventing me from applying it directly to winter data. The thing is, in order to get reliable results here, a reliable well-calibrated probabilities, the machine learning model actually learns about the climatology of how many thunderstorms, the fraction of thunderstorms that are happening that it has been seen during training. And since I've trained during summertime, it is used to seeing a certain amount of thunderstorm occurrence, and in winter there is just much less thunderstorm occurrence. So I would expect my results to be to not be calibrated anymore. I'm not sure if we actually. The thing is, we know about this. Since we know about this miscalibration thing, I think it is enough actually to. It might be enough to just know about the climatology of thunderstorms during winter to recalibrate. Actually, so it might be that this is already enough, but obviously it might work better with retraining. Yeah.
Yes, thank you.
Thank you. This is quite interesting, and especially to the last question now concerning winter lightning. At least in Norway, the weather situations for winter and summer lightning are very different. And also, so that would make me think that it would not yield good results for winter at all, because also the physicality is not not really the same. I mean, in Norway, thunderstorms can be just 5 kilometers in height and still give lightning, and the model here wouldn't even look at it. So I would be really careful with that. But it's very interesting. So I would be interested in the results also for other cases than summer. Thank you.
Thank you. About these thunderstorms being different kinds of thunderstorms, this is something. This question comes a lot, and I definitely agree with you that if we have two thunderstorms that have like a different physical mechanisms with different physical mechanisms behind them, then it's and we have trained the model on one type of thunderstorm, then it's absolutely not clear if the model would detect the other one. What we are hoping to do, so we actually trained the thunderstorm. We trained the model on like the entire icon domain and hoping to capture a large variety of different types of thunderstorms. And since we've by training the model on a large region and a large time period, we hope that the model finds the greatest common divisor of all different kind of thunderstorms. For example, if there are different types of thunderstorms, if you stand right in the thunderstorm, you would be able to say this is a thunderstorm, right? It's there's even if there are different development stages of thunderstorms and different types, there's a like global essence in there, like that we hope is caught by the model, but yeah, it's.
But then again, what does learning for a machine learning system really mean? Just because they have a correlation that the model is looking at this parameter, does it really has understood why? Or is it just correlation?
That's a good question. Do we really need the model to understand it like in total? It would be nice, obviously, but maybe we're asking too much of a model that has like 20,000 parameters only.
I agree, but then I would be really careful in using the word learn.
True. Yeah.
Heard from Francisca that we should come to an end because we have to leave for our excursion in 25 minutes and we still have to eat.
Oh.
So,
I can ask a quick question.
Very, very quick.
Later.
Maybe separately.
Yeah.
Thanks. So thanks again. And do you want to have a final?
Just shortly, I don't want to take it from you, sorry. Maybe let's thank all the speakers from today again. Yeah, we were running a bit out of time, so normally we should start 1:20 with the excursion. I'm not sure if colleagues from Met Norway are here, and if it's possible to postpone it a bit. Who said yes? Yes. Do you think we can start at, I don't know, 1:30 or 1:40 or whatever, that you have time to eat, to take your time, because I think we need good food now to be fit for our excursion. Okay, super. Can you inform Solfrid, because she had to leave for a meeting and she will come back? That would be great, thanks. Okay. Let's say 1:40, so that you have 40 minutes from now. Is this?
Ich habe mich nirgends registriert, bei keiner.
Ich auch noch nicht. Wir gehen dann einfach wieder zurück.
Jetzt muss ich wieder aktualisieren.
Müssen wir da noch irgendein Mikro abschalten von uns?
Darf ich fragen, wie habt ihr die Präsentationen kopiert und so?
Na, also jeder Chair.
Ja.
Anscheinend wurde das ja ganz zu Beginn erwähnt, da waren wir noch nicht da. Jeder Chair muss seinen eigenen Laptop hernehmen und die Speakers müssen dem Chair das per E-Mail schicken. Vorab.
Ja.
Ich habe das auch nicht gewusst und mir haben die Leute gestern am Abend geschickt ihre Präsentation und dann haben wir gedacht, was mache ich damit?
Ja, weil zum Beispiel meine Präsentation ist ziemlich groß und der E-Mail verwirft mich das.
Oder mit einem eigenen Laptop, das kann man schnell umstecken, das HDMI-Kabel. Das geht auch. da dazu. Das beim, ich weiß nicht, was er tut, zu lang.
Not at all, sorry. No, 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 no. The faintest idea. It's my first time in Norway. Mine too. It's a great. Is it the network still available? Do you have an experience of this? Do you see if the network is still there? It's guest. You see?
Yeah. But you just need to, I think you need to sign in every year, every day. Because it asked me yesterday.
Can be. Now I try again. Yeah, when I was coming, I was thinking, you said we are going to be there, and what should I do? And then, ma Google a little bit, and then I started jumping.
I think everybody, we are going using public transport. So, where it goes, you can go where outside.
I'm kind of lost whenever I go anywhere. Because I cannot reach anything quando non mi funzionava.
Well, there's a logic there. It helps to know some Swedish. I think so, yes. I think the organizers, or one of them, might know when you go up to the Holmenkollen, is it still so nice?
And it's also so one if you want to go to an island, you can take a ferry
It's
to
a really big area also.
Yeah.
Yeah, but in Sole is the zone.
When you buy a ticket,
I'm calling
it's
the
a
man of
different
the
zones, so it's more expensive. You can have more zones, but it's just so many. I was looking for
Have my 24-hour ticket, which is
So good luck. Molto, molto spiritoso.
Good luck.
Thank you. I have to tell you.
Know about this stuff.
Eh?
Just tell me about this stuff.
He would be happy. Can I remember a new person for the AI?
You have
So.
3 trips and then it's. Did you
He'd
say
be
40?
very happy.
How much is?
45.
Yeah, so
We
3
know what
trips
we
it's
are
already
good
makes
from.
it more.
But today I didn't use it yet because I walked.
Uh-huh.
Because
Are you staying in December? But you know that we will leave in a few minutes.
Sì.
So it's. But das wird ein schnelles Gespräch. Zack. Tschüss.
I'm thinking where the railway is because it's all Hi. Hi, Jan. Nice to see you. I'm fine, thanks. I'm looking for a quiet place. Okay.
National Theatre.
How are you?
Majorstuen, and we have Linda, and then we have.
Good. Nice to